Hello everyone, welcome to part 3 of my reverse engineering and binary modification, patching or augmentation. Without wasting any more time, let me remind you what we were doing in the last couple parts, which I would suggest you watch before you get into this one. We were working with Microsoft Snipping Tool, and in part 1, we actually allowed multiple copies of the snipping tool to work at the same time. And in part 2, if you remember the original snipping tool, we removed this bottom snipping tool is moving banner. So as you can see, the copy that we have here doesn't have this bottom thing. So, and in this part, so what we will do, we will conclude our reverse engineering and binary patching of the snipping tool by starting the snip automatically. So in other words, right now, when you click the snipping tool, and then you have to hit new to actually start the snip. In the last modification, what we'll do, we'll automate this part. So you start the snipping tool and it will automatically start the new snip. Okay, so this is what we will be doing today. In case you're not interested in watching me do all the work, you can download the final product in the description for this video. Otherwise, let's begin. Okay, well, first thing first, let's quickly analyze what we have here. So if we start detected easy and drag a file into it, for some reason, I'm not sure if this is a bug in detected easy. It never works from the first try. I know this is kind of annoying. I'll try to report it later, but for now, let's just live with it. So I am going to do it twice. And okay, so at this point, it tells us that this is Visual C, C++ compiler. And it tells us that we have to analyze it with the binary, with the native debugger, like any of these here. In this tutorial, I will be using two. I will be using IDA free and x64dbg. Now, also you can see that this is a 64-bit Intel or AMD 64 or x64 binary. So this is what we needed to know. Okay, well, at first, let's see how we will actually do this. Now, I tried to reverse engineer the code itself to see if we can get to the function that is called when the button is clicked. And this is definitely one way to do it, by just invoking the function that runs when the new button is clicked, right at the get-go when the app starts. To make it more interesting and to kind of separate reverse engineering and binary patching into three series, I decided to do it differently. If you remember in the first part, it was not that much reverse engineering or patching. It was kind of like a very kind of starter thing. In the second part, we were heavy on reverse engineering by removing the bottom and kind of like analyzing the code and trying to figure out what we need to do and where. Eventually, if you remember, the patch itself was just 1 byte, which was kind of cool in my view. And in this tutorial, we will try to do a little bit of reverse engineering, and we will do quite extensive binary patch. So what am I proposing? Well, what I'm proposing is that when the app starts up, we will simulate this button click, right? Now, I know there is a way to do it using an external tool. I'm not doing it with the external tool for a couple of reasons. Well, first of all, this is the example of binary patching. So obviously, I don't want to use external tool. So I will show how you can do it internally inside this binary, inside this PE file, which is this one. And secondly, when you have an external tool, it's additional dependency, and sending button clicks is not very reliable. So that's why I'm not doing it here. But again, if you prefer external tools, please go for it. Okay, well, before we can do anything, we need to analyze and see how exactly this thing is built. So we know that this is C++, but we don't know how these buttons work, these right here. So the easiest thing for me is to use my WinID tool. If you prefer, you can use Spy++, so it's kind of similar. Now, the way WinID works is that it gives us information in its readout about a control or a window under the mouse. So I have to point the mouse to actually see what's happening. And this is what I'm doing here when I'm pointing at the new button. Now, if you look at WinID over here, where I'm pointing with the mouse now, where it says class, right now WinID 3hex, when I point at the new button, it gives me class toolbar window 32, and on the right, it gives me toolbar class name in red. Now, what this tells me, I kind of take it from my programming experience, is that this control here is nothing else than the common control, which is Windows so-called Win32 control, kind of really old school GUI that Microsoft supported and still supports. And the good thing for us is that this toolbar class name is actually well documented. So before we go any further, let me make a snapshot in WinID. For that, I'm again pointing at the new button here on the snipping tool, and then I hit Shift. And as you can see here on the top left corner, of WinID, it created a snapshot. And over here, it gives us some information. So let me create a new notepad with my work info. I'm just putting all all my snippets here, and let's call it, let's see, new snip, auto new snip. Okay, so if we open it up, and what I'm particularly interested is the class name over here. So let me copy and paste. Remove last enter and make it a little bit larger for you. And I'm also interested in the styles for this control, again for the toolbar over here. And the reason I'm interested is that these styles for the window are actually quite well documented. So as you can see here, these would be, let me just a second, let me just break them up into lines like so. So these would be well-known styles, and these would be extended styles, which makes it really, really interesting for us because we can just implement, we can just look up the documentation for this thing. You see how to create toolbars, and this actually gives us a nice example how, basically explains what these things are, gives us a good example, and also kind of tells us how to emulate a button click. So let's kind of think about it. So first, what I'm thinking is that to kind of better visualize this patch, I would suggest creating a small sample app in Visual Studio and kind of see how these things work, and kind of like, throw it in C and C++, or in this case probably C++, that we can later emulate in assembly and convert to machine code and actually implement our binary patch. So it will be kind of like a several step solution. So the best way to do this, to kind of like emulate it in our own app, is to create it. I personally like using Microsoft Visual Studio for that. So I usually create a little kind of sketch test project. Now in this case, I will need desktop application, and I probably need C++ desktop application, and not the desktop wizard, but this one, Windows desktop application. In other words, this is very primitive Win32 kind of like a template app, so that I don't have to like type everything from scratch. And it's also using C++, and I would call it test toolbar 01 for the lack of better name, just anything that will tell you what this thing is. And no, I don't want to sign in Microsoft. Okay, so right from the get-go, as you can see, it gave us a bunch of code. So before doing anything, let's just compile, build it, and run it. As you can see, it gives us very simple GUI app, kind of like a scaffolding for us to work with. Okay, well, in this case, let's create a simple toolbar. Now, guys, I will not be stopping over and explaining this part because it's actually all, like I showed, documented. If you, again, search for the class name, like over here, there's a small example. I can kind of show you what's being done. So let me throw this in kind of in a quick fashion. So first, what we need to do, we need to create just a simple function. I'm going to call create toolbar, and it will accept a window handle for the parent, right? And over here, I will create a function that will destroy toolbar. Now, it's a good practice to kind of like remove or clear up whatever you are creating. So I will quickly put these two declarations here. Again, I'm not using any fancy classes. It's mostly like C with some sprinkles of C++. We are not really concentrating here on the actual, C and C++ stuff. We're just kind of creating a basic scaffolding. So over here, we need to actually call this function, and we call it from when we create our main window. And let me do it like so. And here we have a little bit of a question. We need to see what we have to return. Let me see. So now if you're not sure, you can just use, well, your trusty Uncle Google to look up this definition in MSDN and look at return parameters. If application processes this message, it should return 0. So this is what we're doing. So we're returning 0. Okay, so that's how we create, and we destroy over here. And again, this is just the basic scaffolding. So again, we destroy it here, call our destroy method, and create toolbar here. Now to make sure it works, let's just put 2 breakpoints and call our thing. Okay, so the create toolbar is called with the actual RCX. Yep, so we get valid, let me just get valid window, and then when everything goes out of scope, again, we get a valid window and everything terminates. Perfect. Okay, so in this case, we don't have to really experiment with anything because we kind of have all of our styles over here. So let's just kind of like copy and paste them. Again, we got this from WinID tool from the actual Snipping Tool. So let me paste them here, and this would be a comment. Okay, so well, the easiest way is just to call create window X. Like if you remember from our first part, we kind of did this already, and then we have the prompt gives us things that we need to type in. So external styles, we don't care. Toolbar, you know what, we can just copy and paste it from over here that we got again from the WinID tool, toolbar class name, and this gives us a warning that doesn't know where this thing resides. So let's okay, so we need to include command control H. Let's do this real quick. And so include command control H. And while we're at it, we'll need a few more libraries, like I will use assert so that I can put asserts to test my code, kind of like in a quick and dirty way. And then we'll also need shell API for one of the APIs that we will be using later. So let's skip down to here. Okay, and let's just finish creation of this thing. So again, let me bring up the prompt. So there is no title, and we need all of these as our styles. Again, I'm just taking it from the current existing solution. Okay, so we don't know where we are positioning it, and the parent is our window. Now this parameter, which has the type HMenu, is the control ID for toolbar. Now we will take it from our WinID. Now the next, well, I'm going to put 0 for now. And the next parameter is the H instance, and we can get it by calling an API, which is get module handle. And by passing a null, it will give us our own H module. And last parameter is lparam, which we don't care about. Okay, now in this case, this call will give us an H window of our toolbar. Let's create a global. Again, I'm not concerned about, use of globals here, because again, we're just doing a throwaway kind of like app. Okay, so before we actually do anything, let's make sure it's not null. And since we created it here, let's destroy it. Again, it's very important to remember to do this as you go. I see a lot of tutorials when people throw in memory leaks. So in this case, we destroy it as soon as we created it so that we remember. Okay, and this last part, control ID. This has to match what we actually have in the actual example. So let me start my snipping tool and start WinID. And when I mouse over, if you can see over here where it says ID, the ID of our actual toolbar is 1. So this is pretty easy. I don't need to make a snapshot. So I put it 1 over here. And kind of let me quickly test it to make sure it works. Okay, and we create something here, create toolbar. Obviously it's not visible because we didn't set the size. And over here we also have its handle, and it returns, as you can see, RAX1, so it means it's successful. Okay, very nice, guys. Well, if you read about toolbars, you'll learn that you can send them a few messages. It's kind of like it's all in the documentation. So let's do that first. And the message we are sending is toolbar button struct size. This is kind of like old Win32 way of telling the library what is the size, what is the version of the toolbar, and we need to send it TB button. Again, this part is just initializes toolbar to the current or the latest version, well, like late 90s probably. Okay, and then we need to add buttons. So again, we need to send message W, and again we send it to the toolbar, and the message is called add buttons. And again, guys, I'm going kind of quickly through it. If you are curious, what you can do, you can go into, again, Google and Google search this thing. And I think over here it actually, over here it actually shows you what you can do, but then you can look at specific messages and see, what parameters it's actually requesting. But in my case, again, I'm doing this real fast, so what we need to specify which buttons we're adding, and let's just say buttons, and do like so, and then when we pass this to our actual function, the first parameter should be count of our buttons, and the second parameter would be the actual buttons. Okay, that should be like so. And then we need to fill out, what I will do, I will put a couple buttons in the toolbar to kind of basically give us something to work with. So if you look at the declaration, we have to have like all these things. So I will kind of like declare them inline. So the first thing, if you go into, again, see what it wants the image. In this case, I don't care about image. I can just specify none. And then it needs button ID. For simplicity, I'm going to put 100. And then it needs state. TB button state. Well, the button will be enabled. Again, we're not going fancy. And then we need special flag that would, instead of showing an image, it will show text. Now then it has a struct, which we don't care about, we'll just zero it out. And this parameter we don't care. And the last thing is the actual text of the button. This one we will call 1. And it has to be converted into int pointer. And this will create one button, and then we just replicate it. We need to give these buttons different IDs and different names, 2 and 3, right? Okay, so this should technically add our buttons, and let us run this thing. As you can see, we have 3 buttons on the toolbar, which is perfect. And one thing that I would add is that let's put some action for the first button so that we can actually simulate it. Okay, in Win32, it's probably done in the window procedure for the main window in the command. And as you can see, they're already doing something here, and they're processing about and exit. Well, in our case, we need to do it in the default clause, because obviously it won't be any of these. And kind of quick and dirty way is to check if our window. Now, if you look at the Windows message command, you'll see that it sends its window in its L param. And we need to see if the window matches our toolbar. And we need to do a quick cast. Okay, if this is our toolbar, and we need to make sure that this is our command, and command ID, as you can see, they're using it as the low word of WParam. Let's just reuse it. If you remember, our command for the first button was 100. And in this case, let me just show a quick about thing for Windows, kind of like what Microsoft does. It's a kind of like lesser known API, shell about. You can look it up on MSNBN. And it needs several parameters. Let's say this one will be my app. I don't know, just something. This will be my info. And the last one, we don't care about an icon. So what this will do, this will give us processing for a button with the ID 100, which is, the button that we just added. So let me show how it works. So if you click button 3 or 2, nothing happens. But if you click button 1, we have this about thing, kind of like, what Microsoft does. So the emulation in this case is when we start the app to emulate button 1 click, and basically it should show us this. Okay, well guys, how would we do this? First thing, as you can see, because we have a compiled app, in our case, the easiest way without doing any emulation is just to put it here, right, in Windows Message Create. But we do not have access to the source code for the snipping tool. So what we can do, we can find the window procedure for the main class, which is pretty easy to do. If you go back to our VM and look up the snipping tool, for instance, with the Windows ID, with the WinID tool, you can hover over the main title bar to get information about it, hit Shift to create a snapshot in WinID, then go to that snapshot by clicking here top left, and then over here you can see that there is a window class, window procedure for the class, and this is the actual address for the window procedure. So it's pretty easy to look it up. So once we have it, we can technically put a patch inside of the window procedure to do our work. Now, because you don't want to go too deep into it, we need to see what is the easiest way to simulate the button click. And the easiest way, in my view, is to intercept the first invocation of window message paint. And when window message paint is called, if I, let's say, remove all the breakpoints and put one here. So what happens is that the app itself is about to be painted. So this is the first time when it's fully on the screen and you want to kind of like to do all the painting code as Microsoft put here. But in this case, if we intercept this message, we will be sure that our toolbar is created, because again, we don't want to call our button simulation when before the toolbar is created. That is why you have to be careful if you put it into window message create. So to go kind of with the easy way, we know that when the window is displayed, the toolbar will be created and we can send that message. So the easiest way for us to do it is in the first window message paint, window message paint invocation, after the processing is done, to be kind of like a good citizen. And this is easy for us to do. So in this case, we can just kind of simulate it at the end of the window message procedure. Now again, guys, I'm not advocating that you would do this in a kind of like a example where you have source code. This is just specifically for the binary patch. Okay, so well, let's see how can we do this. Now the easiest way to simulate something that runs only once is by using a static variable. Let me call it ran_once. Now originally it will be set to 0. If you know about static variables, you will know that they reside in a special section, read-write section inside the P header, unless they are const, but in this case we were setting it as int, 4 bytes. And then what we can do, we can say if it's 0, then do all of our work here. And then when we're done processing the first message, we will set this to 1, so this if statement will never execute. It will also be very simple and very cost efficient, I would say, cost efficient meaning CPU cost of checking it, because this will be very simple CPU instruction, and this is what we will go for. Okay, the second thing that we need to do, we obviously don't want to process it on every iteration of the window procedure here. We need to check when the message is window message paint. And again, guys, in a normal processing, kind of like if you had source code, obviously you would be doing it all in here. But since, again, I don't know where exactly this case wMessage paint is in the snippet tool, in the whatever the tool is called, so we have to do it here, kind of like a second if statement. But again, that's not a problem. Okay, and once we detect this window message paint, we actually need to reset our variable. So in other words, what will happen is that this thing will be called only once, and then if you call it again, it will never be called after the first time. And this is what we are achieving by using the static variable. Okay, well, so what shall we do next? Now, if you know the way relocations work and how compilation works. You probably know that Windows APIs are called through what is called IAT, which is Import Address Table, and when the let's say API is compiled, it compiled into a long keyword pointer to something inside IAT plus offset, right? So in other words, it reads keyword pointer or 8 bytes from the IAT plus offset and then calls that address. This is kind of like a quick and dirty way for Microsoft to reposition the binary and find and kind of place all the offsets to APIs in one location. So these things will definitely have to be adjusted in our binary patch, which will be kind of like the type of shellcode. So, but what this tells me is that we have to minimize the number of API calls that we're invoking here. So we have to be very judicious with those. But having said that, we need to kind of see which APIs we will need. Well, the obvious API that we will need is send message W, right? To send messages to our toolbar. So this is obvious. And what I will also kind of like think about doing is implementing a command line. Now, if we look at the snipping tool, not everyone would want to start, you know, with this particular like button click. Some people might say, hey, I don't really need this, so let me give an option. And the option that I'm suggesting is actually providing a command line for the snipping tool. So if the command line parameter is present, it will simulate the button click. And if the command line is not present, it will not do this. This is also kind of like a good way to show you how you can, you know, put switches into your binary patches. And this is what I will show. So if we go back, so the way we analyze command line is by using two commands, by using two APIs. One is by retrieving the command line itself, which is called get command line W, and the second one is by analyzing it, command line to argv. So this one retrieves the command line, and this one, if you look at API documentation or at the quick prompt, so in the first parameter we pass it the full command line and it analyzes things for us, returns number of arguments which we can hold in like so in number of arguments, and on the output it gives us a pointer to the arguments, right? So this stuff is very similar to argv and argc that you get in the main. To be honest with you, these are two functions how Microsoft is passing argc, so it's like the other way around, argc and argv into your main or win main. Now if you look at the documentation for this guy here, the important thing to remember is that it actually gives us heap allocated memory, and it should probably say here, yes, so we have to call local free on whatever it returns us. So this is very important. So finally we need to call local free on our arguments to actually release them. So, and this I would say would be 1, 2, 3, 4 APIs that we will need to call. And also guys, now the way send message works is that we need to send it to the actual toolbar. Because we don't know the handle of the toolbar, again, in our case we do, because, you know, obviously we put it in a global variable, right? But we don't know where exactly Microsoft is storing their toolbar. That is why we need to look it up by its ID. And we can use get dialog item API to look up handle of the toolbar using its like what the prompt here shows, using its control ID. And we know that control ID is 1. So these APIs that we will need, but then we have to understand, where do we get these from? Now, in case we compile our app here, these APIs will be, processed by the linker, by the compiler and linker, and they will be included in the imports for this module. Because we are inserting this code into already existing code and we're not linking anything, we're not compiling, we have to make sure that these APIs are actually available in the binary of the snipping tool that we'll be working with. So I suggest putting them in a list as so, then just the list of APIs. It's a list of APIs that we need to work with. And really quick, let me just copy them into our VM, and I'm going to use my trusty notepad. Okay guys, and we need to check if these are actually imported into our snipping tool. So how do we do this? Well, we can use my Win API search, and let me get to it. And if we open it in Win API search, so we are looking at imports only, and let me run the search. So in this case, we don't need all of it. So let me kind of expand it. So if we look at the imports in the snipping tool, these, as you can see over here for our snipping tool, and sort by name, this has all the imports that are actually brought into the snipping tool from one of these modules. And let's just see one by one. So command line to argv. Let me just bring it over here and do like so, so we can actually put them side by side. Because it's sorted, let me just go to CO, and so this one is no, because again, I don't see it in the list, right, in the list of imports, because again, the list is sorted, so it's not here. Okay, next one is get command line. Okay, just scrolling down, and let's see, get, okay, this one is also no. Okay, local free, let's skip down to local free. Okay, this one is yes, so it means that we don't need this one, we can actually reuse it. And get DLG item, and let's take a look, and it is present, so yes. And send message W, most certainly this one is present because it's a very popular API, but let's double check. And send oh, skipped a little bit too far ahead. Send message W, and again, so what this tells us, if we take it back into our C++, so what this tells us is that these two functions right here, oh boy, Visual Studio is not cooperating. Okay, so these two functions we have to import dynamically, and these functions we can actually reuse. Okay, well, before we do that, let me just put this up ahead, and first let me write the logic of how this will work, and after that we will actually worry about these two functions. Okay, well, now let me just quickly write it up so we make sure that we actually get a address here, so we don't need anything at the end. And this one is we're analyzing command line, and then we can quickly go through all command lines. And again, we don't really care about any specifics here. We just need to check for our command line parameter. And let me just quickly put it here. Let's see, command, and we use one of our arguments. And just for the simplicity, I will assume that command line argument is 1. Yeah, if somebody specifies 1 as a command line argument, then we will send the simulated click. And the way this is easy to check, instead of using any APIs, remember we're kind of like trying to minimize it to a minimum. We can just check that and ensure that we have a null following it. So in this case, we don't need to check anymore. So in this case, we check that the command line parameter is actually 1, or well, in this case, it's a string 1. Okay, and over here, we need to retrieve our toolbar. And again, if you remember, we have a control ID, which is 1, and H window is the window from the message that we received, so we'll have it, and the window is the main window, handle for the main window, and using it we retrieve control with ID 1, and remember 1 is the ID for the toolbar in a snipping tool. Again, the reason you would know is if you start the snipping tool, just close this. You start the snipping tool, use my WinID, point to the toolbar, and over here it says ID 1. So it basically tells you that we have our control ID, which will not change. And let's create local variable toolbar. And just to make sure we got something, let's assert. Okay, and once we have, we simulate a button click. In this case, on the first button. And the way this works, in this case, you can actually use Spy++ tool to actually observe the messages that we get into our toolbar. To kind of save you time, I can kind of tell you what happens. We basically have a button that has data, and we need to send it to our toolbar. But before we can send it, we actually need to get to fill it in. So for that, we send another message to our toolbar. Again, remember, we can't use a global class. We have to use a local variable that we got here. And we need to send it a message which says get button. And get button, like the first parameter will be the index of the button over here. So let me just put a small comment. Index of the button. In this case, it's 0, so because we need the first button. And the second parameter is our data, and we probably need to cast it to alparam. And this message will return non-zero if it's successful. And over here, let me assert in case we fail. And again, these assertions is just right now for me to see if it's working. Okay, and once we populate our TB data here, what we need to do, we need to send toolbar another message that will basically send it a command. And this is what we are simulating. So command, the first one is the ID, right, that we received for the button. And the second one is our actual toolbar, and we probably also need to cast it to L param. Okay, and this will send command, kind of like what we already did before. Remember, like we processed it here, but in this case we are simulating it. Now, I'm not saying that this is a good programming way to do, but this will definitely work in case of a binary patch. Okay, so let me run, make sure it compiles, and if I run it, I should technically see our simulated button, but I don't, and that's the reason, because we don't have a command line. So if I go into the properties and debugging and command line arguments and specify 1 and then run it, and as you can see, the button gets clicked, so the app is still working. Again, let's try again. As you can see, it's simulating the button click, and right when we start the app, the actual toolbar pops up. Now, just to check, if we put, like, let's say some other command line, it should not trigger, and we can continue using the app. So as you can see, this is the code that we need to actually put into our binary patch. But here we need to address a few things. Now, first, as you can see, these two APIs did not come in the snipping tool itself, even though these three exist there, right? So it's pretty easy to deal with these things, but we need to do little extra work with these two. Let's think how we can actually do this. The easiest way that I know of is by using another API that's called getProc address. The way this API works, it needs a module and a process name. So the module name is pretty easy to look up. We can just do a get module handle, specify the name of the module, and then we need the name of the API. Well, but this creates another problem. By the way, this is get module W, because again, we're working with Unicode strings here. Okay, but this creates another problem. We just added 2 more APIs to our list. And also, by calling get module, we need to make sure that that module is also loaded. So before we can go any further, let me just kind of do these two things and put these two APIs here. First, we need to see which module are these present in. So if we go into our trusted Google and search by first API, we can already see that it's a shell. We scroll all the way down. It tells us that this is shell32 DLL, and this is the module that we need to retrieve it from. So again, let's make sure that this is correct. Get command line to argument, and get command line to argument V. Okay, this is the first one, and the second one is command line, get command line W. So if we search for it, and now this one is a little bit tricky because they put it into a different header file, but the DLL is kernel32 DLL. Okay, we can be sure that kernel32 DLL is always mapped, because again, it's the second module that's mapped into pretty much all user mode processes. But we need to check about this one. And the reason we would do so is because this API, get module handle, will work only if this module was previously loaded. If it is not loaded, it will return us a null, and we will have to use another API. We have to use get load library to load it like so, you know, again, if it's not present. But the problem is that with load library, we have to call free library to actually free the handle that the library will give us. Well, that kind of complicates things, so that's why the easy way would be to see if the module is actually loaded into the process and not reserve and use get module handle instead of using these two APIs. But for that, we just use the WinID search that I showed you previously. So again, if you started, let me just minimize it, move WinAPI here. I will set modules only, do the search, and then scroll it. I'm sorry, sort it. And then, as you can see, kernel 32 is present, and luckily for us, shell 32 is also present. What this tells me is that both modules, kernel 32 DLL and shell 32 DLL, are present in the static linking. So in other words, they will be present from the get-go, and this tells us that we can use this construct to load our APIs. So, but this gives us additional headache because we just got 2 more APIs that we need to be worried about. And the problem is that if any of these are not present in the static linking, like we checked before, we will not be able to use this construct. So let's check real quick. So one is getProc address. Let's go back to WinAPI search, change it back to WinAPIs and modules, do the full search, and in this case it looks for all imports as we specified here. And then if we click on title here, so again we are looking for getProc address. So let's skip down to G and hope that it's in the list. GetProc address is very handy because that function is what will is something that can let us get any API, and as you can see, they do have GetProc address. So we can put yes here. And the second one is getModule handle W. And as you can see here, getModule handle W is yes. And this is a sigh of relief because this really simplifies things. In case, just a small aside, in case you cannot find getProc address in the import table, you would have to resort to writing a shellcode to find it. It's also possible. So if you go to my blog, and let me just search, I think it could be this, or actually this one, I believe, deep dive into assembly language Windows shellcode getProc address. So this blog post will show you how you can actually find the address for getProc address using shellcode, just Win32 assembly. And I believe it's one of the, okay, this is 64-bit, like this one is assembly function that can get you address of getProc address, and the same for 32-bit, without invoking any APIs. But this obviously adds a lot of complexity here, so that is why if you have getProc address in the static imports, this is big saving of time, and this is what you can use. Okay guys, so in this case, so what we need to do, we need to replace these two APIs with dynamically loaded this way. And before we can do this, we need to look up the declaration of these things and do it like so. I don't care about all of these things, so basically it's returning, let me It's Win API. I'm just declaring them like so that I don't have to worry about specifying, you know, basically without calling them statically like so. Okay, let me just clean it up a little bit. And don't need this SDL stuff. Okay, and also for command line. Again, I'm just taking it from the Microsoft declaration. And yeah, let me put it on one line. So it's an API. I usually put PFN in front so that I can kind of like distinguish between this dynamically loaded API and a statically linked one, but you don't have to do it. Okay, and then we need to actually load them. So we're doing it like so. I'm going to assert to make sure that it actually loaded it. And let me break it up into a couple lines. And we need to mute the type conversion and do the same thing here. And we need to assert and do the same type conversion here. Okay, and now when we have these functions, we can actually call them as such. Okay, so and by calling this kind of shebang, making it way more complicated, we're basically loading them dynamically because these APIs are not present in static linking in original Snipping Tool. Before we can go any further, let's make sure that my code here works. So let me do the correct API, and it does. I mean, correct command line, and as you can see, it works. Okay, at this point, I think our primary C or C++ code is working. So what we need to do, we obviously need to compile it in the release build and make sure it also works in the release build. Oh, well, it doesn't because we didn't provide a command line, so we have to provide our trusty one. And let's see, and it does work, and as you can see, the app is functional. Okay, and this is what we actually need to get. Now, guys, the reason I'm switching it to release configuration is because it has to be optimized code. Optimized code will be, machine code will be way smaller. So for us, obviously, we don't have to have a lot of code here to work with. And also, I kind of like, instead of writing all this in assembly, I want the compiler to do all the work for me, and I'll just adjust it at the end. Okay, so let's see, what did we get here? If we put a breakpoint on one of these checks and run. Now, when the breakpoint hits, let me switch to disassembly because we don't care about the C++ code. And as you can see here, all of this stuff is the generated assembly code. Now, the tricky part is knowing where is the end of it, because as you can see, when you actually analyze a release or compile or a production binary, which was optimized, the source code doesn't really match well with what you see in the assembly. So the important thing for us, let me see, to get back, just toggle disassembly. I put a button here for toggle disassembly. You can do Control F11, but this is kind of like my quick and dirty way to toggle between disassembly and C. So again, Control F11, that's what you can do. Okay, the important part for us is to get assembly code for this stuff only. And we have to kind of like isolate it in the machine code. And sometimes, because Visual Studio puts all kinds of optimization here, we might not see it right away. And my quick and dirty way to kind of like single it out is to put some kind of a rarely used API at the beginning and the end, and call it with some parameters that will not do anything. And I'll explain at the end while I'm doing this, and also put it at the end, right? So this API by itself will not, it will just have an error, but because it will be present in the compiled code, it will be kind of like a marker for before and marker after. So right, so now when I compile it and run it and hit my breakpoint, and then when I hit, to go into disassembly, as you can see, this is where my machine code starts. And then if you search for the second instance of this API, this is where my machine code ends. So this is kind of like my way of saying, okay, this is where it starts and where it ends. And the reason I'm using this is because, again, compiler has to oblige and call this thing at the end of my if statement and also in the beginning. Okay, well, at this point, since Visual Studio was nice enough to generate this nice machine code, again, I copy everything from this first marker from before all the way down to last one. Obviously we don't need this API, so everything before, and let me kind of comment it out and then go to the very end. And in this case, I will use Visual Studio as the editor for my assembly code, because this is obviously not C. I will, you know what, hold on guys, oh, here we go. So I basically pasted my machine code, which I copied, into a large comment at the end, and I kind of like editing with Visual Studio, because it gives us a little bit better selection tool than Notepad. And this is where we will actually edit our assembly code. So what I'm proposing here is that we need to modify our assembly code before we can actually build it. And we will build it in an online disassembler and assembler. The one I was using, online assembler, and the one I was using is this one, which is kind of handy. It can let us assemble and disassemble, and we will use it to convert our assembly code into machine code. Now, why am I doing this, you would ask me? Because you see, like over here, Visual Studio had already offered us machine code, so you can just kind of like copy it from here and use it. And the reason I'm doing it this way, in other words, writing it in assembly first and then converting it to machine code, is that whatever Visual Studio gave us is not something that can run. We have to have a few modifications here, and this is what I will try to show here by kind of like modifying the machine code. Now, technically this patch is a three-step process. As you can see, at first I wrote everything in C or C++, and the reason being is that it is always easy for me to write it in kind of like a higher level language, like in this case C, C++. Then, when I built it as release, I created these assembly instructions by again viewing it as assembly. So as you can see, all of these things are x86 instructions. So over here, it's kind of like my quick and dirty way to have the compiler do to kind of like optimize my C, and then I will adjust my assembly code here, copy and paste it into an online assembly, assemble it, create machine code, and then use that machine code to actually do the patch. So as you can see, it's a lot of work here. So in this case, So kind of like next part of this tutorial would be to analyze this machine code and kind of like make it work in a snipping tool framework. And for that, I have to explain a little bit what I'm doing. Okay, folks, so I took a short break. So now let's get back to our reverse engineering and binary patching. Okay, so just to recap, we got this generated assembly code from optimized C++ code. And what we need to do is, first of all, we need to see where we will be putting this stuff. And right now, if you can see what Visual Studio is doing, it's kind of like mixing up C++ code, I mean, with assembly. So we'll obviously remove this stuff. And what we need is this. But before, let's kind of like look at it and see where we will put, this patch in. Now, as you saw, my original patch in C over here was intended for window procedure. And this is where we will need to put it into the snipping tool. And as you can see, I put it at the very end of the window procedure. And the thinking was that, because we are trapping window message paint, or the first window message paint that comes using the static variable, well, the thinking was that I will first let the snipping tool do its painting, for the first time to display the window, before I can actually send my button click emulation to it. So what we need to do, we need to find the end of the window procedure in the actual snipping tool. So, well, let's start from that. So if I minimize all this stuff, so I already have window, have it open in IDA, but let me close it. And just to show it from the beginning, let me take the snipping tool, the executable, drag it into IDA, and let me overwrite the already existing file. So let me just go through. Okay, we need symbols, if you remember from previous tutorials. And at this point, I need to let IDA finish its processing. And when it's done, okay, there you go. So we need to put a breakpoint at the very beginning here on the Win main. So, and we need to start the process. Again, we're starting snipping tool. And the thing that I need here is this address of the Win main. Let me copy it and put it into my cheat sheet. And what we're going here for, we're trying to find WndProc for the main window for the snipping tool. But over here, let me just say that text section is approximately in this at this address. Again, I'll explain why I need this later. Right now, I'm just seeing that this is the address where our Win main is located in the text section of the PE file. Well, at this point, let's run the snipping tool. And here it is. So the process is running. So next, to locate the window procedure for the toolbar, I will be using my WinID tool. And again, if you remember, the WinID shows information in its window about another controller window that's under the mouse cursor. So if I point it at the toolbar in the snipping tool and hit Shift on the keyboard, it creates a snapshot. So let me open it up by hitting 1 here in the top left corner. And what I'm going for is this window procedure. Let me copy it and close WinID. And after that, let me paste it over here. So this is window procedure for the class, but this is technically what we need. Now, WinID is a somewhat old tool. I've written it like long time ago, and at the time, there were no 64-bit processes. Right now, there are, and as you can see, Snipping Tool is a 64-bit process. So what WinID is returning is a truncated version of the 64-bit value. So what this means is that it takes just this part and removes the upper 32 bits. So to get the full window procedure, we have to apply a little bit of a hack here. In other words, take it from the text segment of the PE file for our module, for the snipping tool, and just append it here. And as a result, we will get a 64-bit window procedure. So now we need to locate it with the debugger. Now, important thing is that I still keep the snipping tool running. Let me go back to the debugger, stop it. I have to wait a little bit, so okay. And at this point, since I have the address, remember like what we got from WinID of the window procedure, I need to locate it with the debugger. So first, let me load symbols for the snipping tool, because again, that's a Microsoft product. Then I hit G and I paste my address. And let me see, why is it not working? I'm guessing maybe I don't need to have WX in the beginning. Maybe that's what IDA is complaining. And it is not getting me where I want to be. Well, let's see why. So we can see, let's just copy this whole line. Okay, so this is the segment. And let me look up again. If I let it run, let me use WinID again. Maybe I just didn't copy it correctly or something. So if I make a snapshot in WinID and go into snapshot itself, and here is the window class. And let me paste it here. Okay, so technically, let me just try it again. If we replace this with this, that should be our address. Oh, you know what, guys? My bad. I'm using the wrong window. I do not need the toolbar. So let me again run the WinID. And something got goofed up in IDA, so I have to start over. Again, sorry for that. What we need, again, so let's start over. What we need is the window procedure, not for the toolbar, but for the main window. So let me start over. Okay, so we broke on main. And let me get the address of the main in the text segment. And then if I let it run and use WinID, but not for the toolbar, but for the main procedure, for the main window, make a snapshot here. Because again, the toolbar is not located in the text segment, it's located in a totally different module in common control. Okay, so again, what we're doing, we're looking where I point the mouse at the title bar to get the window procedure for the whole window, hit shift, and then go here, and what we need is this guy, window class, and again it's just a different address, and let me paste it here, and again do the same hack basically. Let me just do like so. Yeah, so you see like right now it actually matches. So what we need to do, we need to remove this, put it here, and this whole shebang becomes our window procedure. Now keep in mind that it will change every time you start the snipping tool. So let me copy it, take it back, stop the snipping tool, hit G, paste our address, and here you go. So this is the actual location of the function. And before we go any further, let me just copy this whole thing so we don't have to do this calculation again. So we'll just have our function name, and we'll use it to look it up in the next iteration. But for now, to see what's happening, let me put a breakpoint over here. Let me make sure that I don't have any more breakpoints. Okay, well, I have one WinMain and I have this one here. Let me run the snipping tool, and it broke on the window procedure. As you can imagine, it will be breaking. This window procedure will run pretty much many times for the window. And at first, let's kind of step through it and see what happens. Now, it doesn't look like it's a really long one, so let's kind of quickly review it. So at first, they call some kind of internal debugger. Again, internal logger. So we're not really curious about it. It's just some constructor here. Now the second thing that they're doing, they're calling this get window long pointer W. Now just to understand what this is, let's kind of quickly Google search it. And here you go, long pointer. And basically it retrieves information about the window. So the first parameter is the window and the second parameter is the index. If you remember the calling convention, the first parameter is passed in RCX and the second parameter is passed in EDX. So the second parameter is this thing here in hex. As you can see, it's a negative value. And if you look at the index, all of them are negative. So to understand what it means, we have to come here, switch to D word, paste it in, and decimal is -21, as you can see here. So let's look at the description, and -21 is this one, get user data. Basically, it's like specific pointer that's associated with the window. And what they're doing here, they store a pointer to the class, kind of like a this pointer, because again, they have to go from static function into actually class function for the window procedure. And I'm assuming that we'll return it in RAX. So again, this is the this pointer for that class. And they check that it's not 0, and that will be jump. Okay, and then they call toolbar blah 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 window procedure inside the class using this pointer, as you can see right here. Again, probably most of the processing is done inside of this function, so it's kind of like main processing for window messages for the snipping tool, and we don't really care about this. Okay, so then as you can see, it returns the result in RAX, and they temporarily save it in RBX, and then they would call this destructor for their logging function. They resume RAX and return. So very simple thing. And if you look at our window procedure here, what we're doing again is we're inserting our patch at the very end, and this would be ideal place for our patch. So what happens is that this part here, the one that I highlighted, is called epilogue for the function. It kind of, you can think about it like it resets or recovers all the registers that have to be preserved. And if you know calling convention, there are certain registers that have to be preserved throughout the function call. Okay guys, just to recap, I made a small cheat sheet. So for x64 ABI, or Application Binary Interface, the calling convention specifies that there are volatile registers and also non-volatile. Now all of these are volatile, which means that you don't really have to save them in the function. So let's say if your function runs, you can reuse any of these registers without worrying about their previous values. And non-volatile registers mean that you have to save them inside the function. So in other words, if you're using rbx in your function, you have to save its previous value and restore it at the end. So what they're doing here, as you can see, rbx, rbp, rsi, rdi, they're like right here, a part of the non-volatile registers. They are restoring them before actually restoring the stack and restoring the value of R14 and returning. So this is where we will actually put our patch. Before we can do that, let's see how it looks like in the machine code. And just to kind of like save us future steps, let's copy all this stuff into our cheat sheet here. Let me scroll it down a little bit. So this would be our original code, and we will put our jump over here. So in other words, we will put our patch in this location. Okay, so we got kind of like where we want to put our patch, but we have an obvious problem. So if you look at our machine code, which should be clear at the bottom here, as you can see, there is way more, there's way more bytes here for machine code than we have originally available over here. Now, if you looked at my previous, in the previous part 1 and part 2 about binary patches, I was able to kind of like replace some of these instructions with clever substitutions. But here we clearly cannot fit the giant, giant patch that we have over here into this space. So in this case, the kind of like accepted way of doing it is to put a jump. In other words, we would put a long jump to our patch over here and do all the work inside that patch, and then at the end invoke these instructions that we substituted. So this would be my tactic. The only thing that we have left to do is to find where we can put our machine code here. Now, there are several approaches to doing this. One would be to reuse existing segments inside of the PE file. And let me kind of like draw real quick to explain like in few words what this means. Now, if you look at the PE file, like for instance, I'm just going to do very simple, very simple drawing. So PE file on file contains of sections. These are just basically just sections of code or like data. And when it's in file, it kind of, to save space, it is kind of like kept in one continuous area, right? So there's 0, and it kind of grows this way. Now, when these things are mapped in memory, they can be kind of like mapped apart, so they don't have to be contiguous, although some of them can be. And so what happens is that they kind of grow out, so there could be like spaces between them. So this is again mapped, and all of these things, they kind of like, okay, well, I'm missing one, so picture that there's another one. So they don't have to be contiguous in memory, and all of this stuff is kind of like properties of the PE file. And what's important for us to understand is that usually the size of these things, they're called segments, by the way, PE segments, is that the size of this thing is usually divisible by the page size, right? So you have page size, and this Yeah, I apologize for my scribbles here. It's very difficult to write with the mouse. But these would be multiple of a page size. So for instance, if you have some code here, it may not necessarily go all the way to the end of the page. So quite often you have some empty space at the end. And this is where some reverse engineers and binary patchers, they put their patch in. In my case, because I actually have quite a lot here, and I don't want to, like, you know, literally try to minimize this thing and try to make it smaller. The easy way for me is to create another empty section here at the end and actually use it for my code here. So, and this is what I will do. So again, this is kind of like a quick description. Let's try to do this. So let me first close IDA. Again, I don't need to save anything, it's just temporarily debugging session. And there are many PE editors that you can use. In this case, let me use this one. Really doesn't have to be anything fancy. So let me open it. If I go into sections, so all of these sections are current ones that exist in this PE. So I just need to add empty section. And like I said, every size, like if you look at the size of each section, it has to be a multiple of page size. So in this case, I will use one page, which is 1000 hex. Again, it's clearly an overkill for me, but you know, in this case, I'm not constrained by memory. So let me name it. Well, let's say text 2, and probably not very wisely, someone named text the section that contains code. So kind of like in the same fashion, I would also call it text in my case. And the only thing that we have to adjust are the flags or characteristics. To understand what these are, let me go into PE file, and I'm looking at the Microsoft page. So if you come here, and then if you search for characteristics, and you can do Control F to search, these flags is what you see over here. Now, for instance, you have flag 20, and that's hex. So if you look at 20, it means that this is large address aware file. And let me make sure that I'm in the right spot. Hang on, guys. No, this is not what I'm looking at. Let's check. Okay, so let me retrace it back a little bit. So unfortunately, this file is huge, and what we're looking at are not characteristics of a file, but DLL characteristics. And specifically, we're looking at section flags. Let me see, it should be over here. Yeah, so we look at characteristics of section and section flags, and these are the flags that we actually need to interpret. So for instance, if you look at value over here for the text section, just copy it here, and just to explain what these are. So if we kind of quickly translate it, so we have several flags here. We have this, and this. So what we have is 20. We have 4, whatever, with a bunch of zeros, and 2 with a bunch of zeros. So if you look at 20, and if we go back to our description here, so this basically says that the section contains executable code. And then if you look at the other flags, like for instance 4000, we can just copy and search. This one, it says that the section can be read. Note that the right flag is not set, so this means that it's a read-only section. And then we also have 2000, whatever that long number is, but that basically means that also this is an executable code. So these are flags for this specific section, and because we are making another executable section, we need to set these flags the same way for our text2 section. Okay, so this will create it. And one last thing, to be able to find it, let me put some identifiable bytes here. Like for instance, I will do 1, 2, 3, 4, 5, something that will let me quickly find it in a hex editor, so I don't have to, like, you know, count the address, offset, and such. And this will do it for now. So let me overwrite original file. At this point, it is important to test that our modified snipping tool runs, because as you can see here, we actually increased the file size. So let's see what happens. And it seems like it is running. And what is important, guys, if you remember in the previous tutorials, I was using my WER setup tool, and this is for Windows error reporting. And it was set up for C crash dumps. That's where it would put all the crash dumps. So what's important is to open this folder and to make sure that there is no crash dumps after we run our modified snipping tool. And as you can see, it seems to be working with our new section. So, okay. At this point, we actually provided the whole, you know, page full of space, a new section in the snipping tool to put our machine code in. But at this point, we need to see how we can modify. Now, the main misconception that many people make is that they compile something in one process, get machine code, you know, for it, and then just blindly dump it into the new process and expect it to run. Unfortunately, this is not the case, and this is what we need to address here with our machine code. Well, let's go line by line and see what is happening here and how we need to address it. Now, the first thing to notice is that we have a static variable here that we are reading and then writing into. So remember, the first thing, we compare it to 0. And by the way, over here we can see that EDI is 0, so we need to make a note here that EDI equals, let's see, assumed to be 0. Because again, over here, if you remember from our C, it's compared to a 0. So over here, we see that there's a comparison of that global variable, and if it's not 0, we skip through the whole thing until we get to the very end. And the very end would be over here, so let me put this instruction here, this address here, so that we can refer to it later. Okay, so we kind of like go all the way, like, you know, what we had in C, if our variable is not 0. So the first thing we need to do, obviously, because in this case we took it from our, you know, this binary here, in Snipping Tool, this address will not be the case. Usually what happens is that global variables, writable global variables, are placed in its own section, and this is a read and write section. So in this case, we need to make a mental note. First of all, we need to make a comment here, and then what we need to do, we need to specify where this address will be in our in the Snipping Tool. Now, the way I would use this, I would use so-called relative programming, because in x64 they kind of changed it from x86, so there's a lot of like relative instructions which basically use the RIP address and some relative offset. At this point, I don't know the offset, so I'm going to use this placeholder that we will fill in later. But the way these instructions work, if you use something like RIP+, it takes the address of the byte following this instruction. So right, like over here, we have a compare instruction. So whatever the address is of this byte following it, it adds an offset and reads from that memory. So in this case, we kind of like specified that this is our global variable, and I see that it's actually written over here to the same address. To make things a little bit more easy for me, I will reuse one of the volatile registers. In this case, let me use RAX to place the address of the global variable into. So in this case, it will be this. And then I can actually reuse it in the compare instruction and in the move instruction. So what it will do is that I don't have to specify this offset in two places. So what I'm doing, I'm loading effective address basically into RAX, which kind of like what I explained, RIP plus offset. So it will give me the address. So it will be RAX will be address of this global variable, and then I can reuse it here for indirect reading. And also, if you look at following instructions, right, the RAX is not used anywhere. So I can kind of use it for this move instructions to put one into it. Okay, so at this point, let me remove this, and let me also remove this. So I'm kind of slowly removing C++ code so that it doesn't, interfere with our assembly. Okay, well, next thing that we need to address would be all the local jumps. If you look, this is a short jump to, well, over here we have the address for it. So if you kind of search, this is the end of the file, and this kind of makes sense, right? If we don't have our 0, it just jumps at the end. Now, to make sure that it compiles with disassembler, we need to replace these with some labels, and I'm going to call it label end. And what I'm using is the mnemonic and syntax for the assembly language. So for instance, this would be label end and label end. And what I like is that in Visual Studio I can use find, and kind of like it will highlight it for me, so it kind of like really helps. Okay, so at this case we can just say label end, and it will take us to the end of our assembly code here. Okay, so let's look at the next instruction, and this one is kind of interesting. As you can see, they are using lower 32 bits of R14 register. And if you look at our original C++, it's this code. So basically, message is assumed, like over here, to be in R14. So let's make a mental note of this. So R14 is the message, and well, let's just say lower, because they're not using the full thing. Okay, and then we have another interesting thing here. As you can see, if you remember, we were loading the module, and we were passing the first parameter as the path of the shell32, not the path, as the name of the shell32 DLL. Well, we have to also address this instruction here. Now what they're doing, they have a read-only text section where all the text and kind of read-only stuff is placed in, because this address obviously is in our test toolbar1 CVP or PE file. We cannot use it in our snipping tool. The easy way to do here is to place this thing at the end of our assembly code here. So what will be happening is that here there will be return instruction, right? We will fix the, let me just do it right now so I don't confuse you guys. So if you remember, we had our closing stuff here that we actually took from the original function. So we have to run this thing at the end. So technically it will be over here, and let me kind of remove this and mouse over a couple times. So this will be the ending or the epilogue of our shim here that we took from the original function. And what we need to do, we need to remove this IDA stuff so that it can actually compile. And you know what, guys? Sorry, this is IDA. I have to change this because it can't be taking them all from the same, from the same bullshit here. So what I need this. I need to put it here, but I need to convert it into actually good and readable machine code. So if we go back, let's see, where's my browser? If we go back here, go into our assembly and switch to x64. Disassemble it. So these would be the actual machine instructions, right? And not this stuff, none of this nonsense. So okay, so these are the instructions that will be actually compiling. Let me remove this. Okay, so yeah, these are the correct offsets because obviously these can't be the same. Okay guys, so this will be the ending of our shim. And before we do anything, oh, I'm sorry, we need to place these strings at the end. It's kind of like not the best coding practice for assembly, but for the shim or for kind of like shell code, that would be quite doable. So in this case, we have to adjust it for the syntax of the assembly that I'm using. First of all, we have to create a label. Let's just call string, and the label ends with the colon. And the way that assembly works, syntax works, we have to start it with the ASCII and then specify our string. But there is a small caveat here. If you look at the string, the presence of this L in front, it tells me that this is a wide string, and the wide string contains 0 at the end. Now the way we can encode it is by using a slash and then the octal value for the value, so in this case 0, and let me place it after every character. And also this has to be an ASCII string that is 0 terminated, so at the end we need 2 more zeros for the null terminator at the end. And again, we're using 2 zeros because it's a wide string. And there is one quirk about this online assembly. For some reason it does not accept any periods inside of strings. It's probably a bug, so to bypass, we need to remove this string and actually encode it into an octal escape value. So let me show you. If we search for ASCII table, and for instance, let's just, I don't know, go to this one and look for a period. And the period in this case is here. like you see. So the octal will be 056, again where I'm pointing with the mouse, kind of like, unfortunately I can't select anything. So 056 is the octal value for the period. And if we go back, so what we can do is put /056 to encode the period. So what this thing pretty much does, it encodes shell32 DLL as a wide ASCII null terminated string. Okay, so as you can see, there is more to it. We also have another string, which is command line argument, whatever, v. Now the difference is that this string is actually ASCII or 8-byte, which we need for getProc address, so this one would be easier to encode. Again, let's do it at the end. So let's create a label for it. Now we need label so that we can refer to it later. And the only thing we need to do, we actually need to put a null terminator at the end. And again, this is kind of like a by convention. Every string is null terminated. That's kind of like used in C and C++. And this is what we're doing here. Okay, well, this is not it. We have more strings. Okay, so we have command line here. Oh, you know what? I think I kind of skipped a little bit. So we have shell32 get command. Okay. Then we have kernel32, which is wide string. Now it's important to encode all this stuff correctly, because if we make a mistake, we'll have to come back and redo it later, which obviously won't be nice. So we're just following the same syntax, and I have to put zeros after each character. I know it looks kind of funny when I do this, and then I have 2 at the end. And I also have to encode a period, because the assembler doesn't like it. Okay, and I think we have one more string, which is get command line W. It's kind of like a last name of the API, so let's encode it here as well. And pretty much do the same thing, create a label, then make this encoding for the assembly. And in this case, because it's just an ASCII 8-bit character, we don't need to make a wide one out of it. And we put, the only thing, we just put 0 at the end. Okay, so let's save our work. And this looks like our strings. Again, because we put them here, we can easily refer to them using relative instructions. So let me show you how you do this. So for instance, here, when we get our shell32 DLL, all we need to do is just RIP plus our label, right? So this will create a instruction relative offset that we can use without specifying the hard-coded address here. Okay, so let's do the same with the other ones. So let me get to it. So we have our let me just get to it. Okay, we have another string. We do the same thing, RIP plus. This is not necessary. Okay, we have one more. We have kernel32. Let's just skip down to it quickly. And we do it here. As you can see, guys, it's a lot of work. You can't just like plop your code into, into a new process and assume that it would work. Okay, so last one is get command line W. And it's this one here. We're doing the same logic, RIP plus. And this way we will encode our strings. So let me remove this. Okay, so RAX here is again the address of our global variable. We set it to 1. And the next thing is the call instructions to our APIs. Now, just to kind of quickly explain how this works, when you have a call instruction, let me just explain it here into our notepad. And what happens is that this thing is the address in what is called IAT. And IAT is Import Address Table. So it kind of like, if you picture it, if you draw it, if you write it in C, it would basically be for procedure API 1, then for procedure API 2, and so forth. So basically our get handle is somewhere here. Now obviously this table is fairly large, so there's like a lot of functions, but basically this is a table where you have like 8 byte slots for each API. And what happens is that when the module is mapped into a process, the loader sees these functions in the PE header, and then it maps all those modules into the file, into the module, and into the process, resolves these APIs using something as getProc address, and puts addresses inside of the IAT. So, and what happens is that the call instruction, for instance, over here, it can point at this address in IAT and get the address of get module handle, and then read it indirectly because of the square brackets, and then go to it. The reason Microsoft or many other actually compilers are doing it is that this is pretty easy to relocate. The term is relocation when they put all these addresses dynamically. And it also helps because of the caching, and it's also really nice to keep all of these things in one spot. In our case, though, we need to find an offset to this IAT from our text2 section. Remember, our call will be coming from our section that we added at the end. So what is important is for us to find the offset, and in our case it will be one of those IP relative offsets from the address after this call instruction. So, and this is what we will be doing. So in this case, let me get this out of here, and I will do RIP plus the offset, and over here I will actually specify which API we're calling. So let me do the same thing with the rest of them. And the reason I'm putting it into comments is so that later on we can fill in the actual offset. So here, and here we have get proc address. Okay, and what I'm putting inside is this little placeholder here that will tell us that later at the end, when we're done with this kind of main schematic, that we have to calculate these addresses and actually fill in all of these placeholders. So, okay, well at this point this looks kind of good. So we get strings and we call these APIs over here using our relative offset to the import address table. Okay, well at this point we have, so RAX will be the result of retrieving get command line API, and then we invoke here. And next one, basically we're doing this, and the next one will be RBX, and RBX comes from over here, and that's the result of command line to argument, like if you see here. Okay, and in this case it actually takes one parameter, which is args. Now args, if you see here, is a local variable. So because, well, Visual Studio is kind of like hiding it from us, so if we took the machine code and then went into our trusty disassembler and then disassemble it, so what we would get is this instruction, RSP plus 60. So in other words, where you see RSP, it means that it is using local variable. So in this case, we have to also think about it. So let me just put it here. And the way you address it is RSP plus some kind of offset. So again, we'll get back to it later. So what is important for us, though, let me remove this, is that we store our args somewhere on the stack here, and then we call API. We put the result, so RBP will be our pointer to the command line that we retrieve. Okay, and here actually check that it's not 0 and, you know, leave the if statement. And over here we have our for loop, as you can see, and call our arguments. So let me put a small comment here, and this will basically tell us to fill in the arg offset here and here. Okay, so over here is just checking that it's not 0, and there is another jump. So let me see where exactly it's jumping, and it seems like there are several of them. Oh, okay, this is the address where we call local free, so we need to make another label here, because it will be important for us to actually call our local free to free up memory. And in this case, we can just replace this with label free, and I think we call it somewhere else, label free. And let's make sure, yeah, we call it in other places, so let's make sure that we do it everywhere. Okay, so let's get back. The easiest way is just to search by label free. Okay, so if we get a bad result, which is, okay, if it's less than 0, we basically don't do anything. This one is just a little bit of a filler before the for loop. Again, we don't really care about this stuff. Okay, so here we check for our command line to be 1. If you remember, 31 in hex is the value 1 in ASCII. And then we also check that the next word is 0. And here we have a couple more jumps, so let's put labels for them as well. So, okay, I don't know what exactly this is. Let me just do label 01. It's just if I don't really know what exactly is happening, I'm just using kind of like generic labels. And let's see if it's used anywhere else, and it's not. But then we have this jump, which we also need to address. And this one is used just in 2 locations. And just for the heck of it, let's call it label 2. Like so. And let's use it for our short jump here. Okay, so let's remove this C++ stuff. And then we have another jump. Again, we have to replace it with the label. Oh, in this case, it's just 2 of them, right? Yep. Let's just call it label 0. And I kind of see what is happening here. This is just basically a for loop. Kind of like jumps back to it. Okay. So, okay, there's offsets, the stuff that it's doing here. Let's remove this C stuff. Okay, we have another API that we need to fill in the offset. And I'm just using this kind of placeholder for now so that we at least have some semblance of a compilable assembly code. Okay, and then it seems like we have another local variable. Again, if you take this into a disassembler, as you can see over here, we have RSP plus. So that basically tells us that this thing here, RSP plus some offset, is our local variable. At this point, again, we're just putting an offset, so we're not doing anything. And then we're calling send message, kind of like what you see here. Now, send message is another API that we have to fill in the relative offset for. So, let me remove this. Okay, so we're sending this message, and this is send message to the window. And we get window in RAX, which is result of get dialog item, and for ID 1, if you remember. Okay, and if we fail, we go to free, and then over here, we need to send another message. So let me put another comment, right? And obviously, we have to provide a relative offset for it. And we are taking this data as some offset on the stack. So again, we don't know what exactly we're doing here. So let me just put a comment and remove all the C stuff. Okay, so we basically read from this local variable and pass it into another send message. And at this point, we are done. Yeah, so we're calling free. That calls local free. So it's another API that we have to find using relative addressing. And if we remove all these curly braces, so yeah, then we come to the end and we are done. Okay, so let's save. For now, we have somewhat, decently compilable, I would say, assembly code, obviously with the exception of this stuff, but we'll remove it later. So at this point, yeah, we just need to fill in all the offsets here. So before we do that, let's kind of try to remove all the machine code, because again, that will be in the way. So let me be careful and not remove something extra here. I'm using Alt, when I drag the mouse, I hit the Alt key so that the Visual Studio lets me do this kind of square selection. And let me just make sure I'm not deleting something that shouldn't be deleted. And make sure I got all the labels. So label 1. Yeah, if we don't have the correct labels, if we delete something here, we will have to recreate it, which would be bad. So make sure you don't remove something that's not supposed to be removed. So like so. And let me delete some stuff here. Okay, so at this point, this more or less resembles some assembly code. And as I mentioned, we will need to fill in these things. But before we do any of that, we need to actually see what are we doing on the input here. Because again, we took this chunk of assembly code from one executable, but we will be putting it into another one. So that creates a little bit of an issue. So we see that over here, EDI has to be 0. So what we can do, we can actually set it to 0, right? Now R14 is our message, and also there was something else that I forgot, and in this case, this call. Now if you look at get dialog item, let me just quickly search for it. The first parameter for this call is actually a window, and the second parameter is the ID of the control. Well, the ID of the control is 1, but what the function is expecting here in RSI is the actual window handle. So let me check if it's used anywhere else, and it is not. So what I forgot to check here or mention is that RSI is H window. In other words, this is what is passed, what this code snippet is expecting. But we don't know if these things would actually match the actual window procedure. Now, if you look at the definition of the window procedure in the documentation, just a callback. So as you can see, Microsoft is great at naming things, but we can kind of tell that the first parameter is the window handle. The second parameter would be the message, right? And then it gives us other parameters. So basically, we have to get these two things from the window procedure from the snipping tool. So, and that's what we forgot to check. So to do that, we have to load it back up in the debugger. I'm going to use IDA. And in this case, it's like really simple. In our case, we actually have the name of the function that is the window procedure, so we can easily locate it. But before we do that, we need to put a breakpoint on the beginning, started, and when it breaks, we need to load symbols for our main snipping tool. Double click, Control F. Before we know this, find the function, put breakpoint on it, run it, and when it hits, so again, according to the calling convention, the first parameter is window. So let's see what happens to it. If you remember again from the previous tutorial, I think it was multiple instances, yeah, like over here. The calling convention, x64 calling convention, the first parameter is passed in RCX and the second parameter is in RDX. So in our case, RCX contains the window handle, but as you can see, they later override it. But before they do it, they place into RDI. And RDI, if you see, is one of those non-volatile registers that they are reusing because, you know, they're saving it here. But what's interesting for us is that they keep the window handle in RDI. Let's see if they override it later, because obviously they're free to do that. As you can see, they're reading from it, reading, and by the time we get to our epilogue, the one that we're actually calling, so in other words, our jump would be on this spot, RDI is not overwritten. So what we can assume for our case is that RDI is the window handle. And so what we're doing here, we're taking the window handle from RDI and putting it into RSI, where our little code snippet expects it to be. Technically, we could have refactored it and kind of like removed and replaced our expected RSI into RDI. But to be honest with you, I don't want to do it, because then we have RDI to be expected 0, and it's much more easy to just do it this way. Because again, this code will run only once, so we don't really care about efficiency here. And the next thing that we need to do, we actually need to set up our 14 lower 8-bit of R14, and that would be the message. Again, if you look at the documentation, the message is passed in the second parameter, which would be RDX. And over here, as you can see, RDX, so its lower part, is put into ESI. And let's see if they use ESI anywhere else. They compare it and move somewhere else, and no, they don't use it. So this means for us that we can take ESI. Again, ESI is the message that they took from EDX on the input of their window procedure, and ESI is where they kept the message, and we need it in R14D, and that's what we did here. So on the input of our function, we will have all of those intrinsic registers set up correctly. Okay, so at this point, I guess we should start filling in our offsets. As you can see, there are quite a lot of them. So let's go one at a time and see what we can do. Okay, well, the first one is the global variable, if you remember our gnRanOnce. And because this is the variable that we will be reading and writing into, like over here, and also I forgot to put a comment here, because remember, like, we put the address into RAX, read it here, and then write 1 in case it's not, in case it's 0. So how do we, where do we put this variable in? Now, we can't just put it here at the end of our code segment, because this is a read and write variable. And the only way for us to put it is in a special section inside of the PE file. So let me kind of show you real quick. Now for this, I need to close IDA and open our snipping tool in another debugger, which is called X64DBG. And just, kind of like to show it a little bit. Before I do anything, I need to modify the font so that you can see a little bit. I'm going to set everything here to 12. Now this part is really nice. I just wish they allowed to do them all at once. And it's just, again, to make it more readable for you. Okay, so if you go, when we open this snipping tool in it, if we go to memory map and scroll down, over here we can see all of our sections, like the text section, like as you see here, executable code, and then also text 2 that we added, also executable code. Over here in this protection column, they have flags, basically protection flags for this, for each section. As you can see, the text section is executable and readable. In other words, it's read only and you can execute it. And our text 2 is also executable and read only. And the rest of the sections are pretty much read only except this one. And this one, the data section, is the one that is read and write, and this is where we will put our variable. First of all, before we do anything, let me kind of copy all of these. So we have, let me make sure I copy like that, and then copy line, And then over here at the bottom, let me, oops, no, that's not what I want. Okay, guys, hang on, I'm just trying to copy everything with the correct formatting. This is kind of like my main pet peeve with this debugger, by how much weird like stuff it has here. Probably crop table. Let me try one more time. Okay, so, oh boy. Okay, guys, so let me work on it. So basically what I'm trying to copy is just selected stuff here. So give me 1 second. Okay, guys, so I basically ended up like just adjusting it in Notepad. This is one of the reasons why I don't like this thing. Because, you know, like when you try to copy, it's like good luck deciphering this thing, right? So anyway, so we got all the addresses, and this would be important for us to calculating offset. So if you look at the data section, the one that has read and write, let me just highlight it like so. So its offset is this, and it has the size of this, and this is obviously hex numbers. So this is the size of the data segment. Something tells me that they're not using all of it. So let me just try to kind of do quick math here. So if I do this plus, let's just do 3, 4, 4, 3FF 0, just a little bit before. So this would be the address. So then if we go back into debugger and click Control G to check the address, as you can see at the end, there's really nothing here. So if you remember my drawing of the sections in the PE file, quite often you use only the beginning, or the compiler uses only the beginning of the section, and the rest of it is basically aligned up to the size of the page. So in this case, because we can safely assume that there's nothing here at the end, I suggest placing our variable over here, and I will align it on 8 bytes to kind of like follow the alignment pattern with the 64-bit CPUs. So again, we'll put it right at the end of the data section of this one with the read-write protection. And to calculate it, we can just do simple math, -8, so that will be the address of the almost at the end of it. And if you remember, our code is actually placed in the beginning of the text section. So if we take our text section address, and because it's, you know, ahead of the data section, so if we subtract the beginning, then add the size and kind of step back by 8 bytes to give us some room, this would be the offset from the beginning of the section. And just to make it more digestible, let me calculate what this thing will be. I will use my test project here, and what I will do, I will just create some variable here and do a quick calculation and let Visual Studio actually do it for me. But hold on, before we do this, I actually want to switch to debugger build. Again, I don't want to deal with like optimized code, because it might actually remove my line here. And if we step over, this is the actual offset. Okay, so let me comment it back. And if you remember, our assembly code was at the very end. So let's see. Okay, well guys, let me paste this offset here as a hex value. So this offset will be from the very beginning of our code section, right? So-called text2, so that's where it begins. So to make it easy for me, let me put the label begin and specify this offset as such. So let me quickly explain what this thing means. Now this is kind of like a quirk of the assembler that we'll be using. And what happens is that, again, RIP, it's a relative addressing. Basically, it will be using the offset from the address, the first byte of the next instruction. And by adding this begin label, which is at the very beginning of our code section, we're kind of like tying up this further offset to the beginning. So in other words, remember like when we did our calculation here, we calculated it from the beginning of the text section. And what we're doing here, we're basically saying, okay, we have this begin thing and then subtract this many bytes to get the address where we will put our run once. So, and the reason we subtract, if you look at the layout of our text section, the data section precedes, or its address is less than the address of our text section. That is why we are subtracting it here. Okay, so this will cover our run once address. So next thing, we need to actually look at these APIs. And the way you get the offset, so basically we need to find, if you remember my previous explanation, we need to find where in the IAT, in the Import Address Table, these addresses reside. The easiest thing for me would be to use a debugger to actually tell where these things are, instead of, I'm sure there are some tools that can probably do it, but again, for me the easiest one is to use debuggers. And if you remember, I actually had these APIs in here, so it's like 5 of them. So let me go back and check. So it's like 1, 2, 3, 4, and 5. Okay, so at this point, let's save our work and go back into our VM and locate offsets for all of these APIs in our debugger. Before we do anything, we need to kind of locate where these functions, which module these functions are located. So we can kind of go into MSDN and see. Now this one is kernel 32. So again, let me just do a quick copy and paste here. I believe this one is also kernel 32. The way you do it, again, you go to MSDN, scroll all the way down. Okay, kernel 32. And I believe getProc address is also kernel 32. Let me double check real quick. Yep, kernel 32. And let me kind of group them together. And these guys, I believe, would be in user 32. So let me double check. Again, these steps are kind of tedious, but it's important to actually get them right. So you have user 32. And let me assume that this one as well, it's a send message. very bottom, and yep, user 32. So to find these APIs, let me use x64dbg for a change. So if we go into let's say, think symbols. Now, again, there are many ways to do this, and probably you'll correct me, but for me, I just go one API at a time. Type it in here. Oh, sorry, I need to locate the module. In this case, let me sort user 32. Here you go. Now we need the first one. Right-click, toggle breakpoint. And then we need send message. Again, the same module. So right-click, toggle breakpoint. Then we need to go to kernel 32. And we need local free. And let's toggle breakpoint. And we basically need to do this for all of them. In this case, it's easy if it's the same module. And the last one is this one. Okay, so, and we toggle the breakpoint. If you go to breakpoints, we should have 5 of them besides the first one. And at this point, we can just run the executable and wait for the first breakpoint to hit. Okay, so we got, oh, we still have the first breakpoint at the beginning of the module, so we don't really care. Let me kind of move this a little bit this way. Okay, so we stopped at get module handle. In case of x64dbg, it has kind of quirky way of stepping out of the function. So when you click it, it gets to a return. And then you have to step it one more time to actually get to the call that invoked get module handle. So okay, and I think we found get module handle. The important part for us to check here, guys, is that we are actually in our snipping tool. If you go into memory and look at, you know, all the modules that are kind of like mapped into this process, as you can see, each of these modules has its own import address table and its own set of imported APIs. So in our case, because our section is in the snipping tool module, the import address table has to be in this module as well. Because, you know, otherwise, if you get import address table from any other, let's see over here, in any other module, they might not be in the same location when you run the snipping tool again. So that's why we need these APIs to be called only from our snipping tool only, or in our text section. So in this case, as you can see down here, it was called from our location. And in this case, so what we need to do, we need to get the offset, and we can do it by selecting the line, the call line, by going binary, copy, and you will copy these machine code instructions. Then we can go to the assembly, disassemble it, and get the actual offset. So this is what we need here, because again, the debugger doesn't show us the offset here. So you can kind of get it from these bytes, but it's better to just do it reliably through disassembler, because if you make mistake, you know, you'll basically pay for it later. So let me place an offset here, and what I will do, I will put offset. Okay, so again, this is let's make sure it's the correct function, get module W. And what we also need is the address of the next instruction. So let's copy address, this one that ends with 3C89. And let me paste it here. And address of next instruction. And this will be important for calculating the location. In other words, we will add this to this to get the address of the import address table. And before I do anything here, we need to save all this stuff again. And again, guys, I don't know exactly how you're doing this. I'm assuming line, full table. Yeah, I have no idea, so I'll just have to crop it and get back to you. Okay, so again, had to edit it out in Notepad. So I basically copied these offsets that we will need for these calculations. Let me paste it here. Okay, so we got one API. So let me go into breakpoints and again, get module handle and disable it so that we don't hit it again, and then run our executable. And we got get proc address. Let's step out. Again, we have to do it twice because of this quirk in the program. And again, as you can see here, we are inside of our snipping tool, which is good. Let's binary copy these instructions here to get the offset. Paste it here and get the offset. And if you remember, the instruction in the call is get proc address, so it's this one. And what we need is the address of the next instruction, which is this one, 3CBC. We go copy address and paste it here. Next step is go to breakpoints and disable it and run it. Okay, we hit on local free. So again, we're stepping out and go through return. And at this point, we're here. And again, over here at the bottom, we can see that we're in the snipping tool, which is exactly where we want to be. So let me copy instructions. Again, just repeating the same thing. So we got our offset, which is a little bit larger, I believe. And let's see, what was the instructions? Local free, the API. Oops. So this is offset, but let's get the the address of the next instruction, and 32D4. Now, important, guys, is to copy it correctly, because if you make mistake, your patch is not going to work. Okay, so local free, let's disable it. So we have 2 left, and let's get going. Okay, we got hit on send message, and we're doing the same thing. Return, step over, and let's see where we are. And in this case, guys, if you look at the bottom here, you can see that we are in common control 32. So what this tells us is that we are in the wrong location. The problem with send message W is that it is used by a lot of other components, not just, your own. And this is kind of tricky to catch it to be called from this module. So if we, let's say, run it again, step out, and scroll up, we're still in some other module that we don't need to be in. In this case, what is nice is that we can set up a conditional breakpoint. So what we're interested in is that we are returning to the module that we need to. In other words, in our case, because I actually copied it here, we need to return into this text segment. So we need to make sure that our return address is within this range. So how do we do this? Well, if I run it again, So as you can see inside of my breakpoint, if you look at the stack, this return address, the first 8 bytes on the stack would be the return address where we are returning to. And if we check it to be within the range of our text segment, right, where we have to return, to get the correct import address table, in that case, we can put a condition for our breakpoint. So let me show how you do it. If you go to breakpoints and edit and break condition, so what we do is memory at RSP has to be greater or equal this value, and let me make sure it's a hex value, and the same memory at RSP has to be less than this value plus the size of that segment. And remember, the size is this. So this is the kind of like paste it here and remove these spaces that the calculator is adding. Okay, so this way we will ensure that when we return from send message, we get the breakpoint when it was called from our text segment. So let's see if it works. Okay, and let's see, where did we hit? Let me just try one more time. Let's see, I'm not sure what happened here. Send message, are we already in there? Let me just double check. Oh, here you go. As you can see, the snipping tool is the one that called us send message, and this is the right location. So let's do the same thing as before. So we need to copy binary data. Now guys, this is very important what I showed here. If you need to get the right offset, because otherwise you'll get an offset from a different module and your patch wouldn't work. So this is send message. So this is the offset, and let me look at let me copy the address, A3F8. Okay, and we need to disable that breakpoint. And one last one is get dialog item. At this point, let's hope that it's called from our module, and if it's not, we'll put that conditional breakpoint on it. So let's run it. And it seems like, yeah, it didn't hit that breakpoint, but keep in mind that you need to locate where exactly the execution path can take you to actually hit that breakpoint. So what I would do, I would go to like a few things, just invoke a few functions, and here you go. So we just found it. Let's step out and make sure that we are in the snipping tool, and we are. And one last time, let's copy the binary, the machine code to get the offset. And here is the offset. So, and that's get item. And one last thing is the address of the next instruction, which is this one, C054. And over here, so now we have enough information to actually calculate offsets for our assembly code. Okay, well guys, having these offsets, we can actually calculate some we can calculate our offsets needed for a function here, but I'm going to do it quickly. Let me do it here in a Visual Studio. So if I kind of format it, so basically instead of calculating it manually, let me just do it like this in the program. So we have uint offset and ulong pointer, and let's just say vals. And let's just copy them from here. What I'm doing, I'm just trying to write a simple program that can calculate the offsets for me instead of plugging all that stuff into a calculator. So again, I created just a simple C struct with offsets and pointers, like all 5 of them. And then let's just do a simple loop. Let's see, I less than count of. Right, so and then let's say we get final pointer. Let's call it V for the backup. Better name. Again, this is not a production code. It's just kind of like a little test case thing for us that won't run more than once. And okay, so what I'm doing, I'm adding this address to this. It will give me the location of the, let me call it right. Let's say address in IIT, address of API in IAT, not easy to say. And then, if you remember, our location here, so our layout here, so the text 2 section is here, and our IAT is somewhere before. So what we need to do, we need to find the offset from the beginning of the text section to the address that we just calculated. So, and what we can do, let's say long, and let's just say needed offset would be this hard-coded address minus wherever that API is. Because again, the reason I copied all this stuff is to tie up the location here, the actual locations of the address here. Because again, we need an offset, we don't need the actual address. Okay, and then we can just output it. Well, let's say output debug string W, and it needs a buffer. Let's just do real quick char buffer to 56, and we need printf type function. Printf, just use safe buffer, size of buffer. And so what we also output here is the value for the offset. Okay, and technically this is pretty much what we need. So all we need to do is just call this function somewhere from here. expand it a little bit so I can actually see what's going on. Oh, identifier not found, obviously, so let me declare it up ahead. Okay, and there's some other issue there. Let's just try real quick to resolve it. Function does not take 0 parameters. Obviously, it needs to have this. Okay, so now if we run it and hit a breakpoint over here, these things would be our offsets. The only thing, we need to match them to the actual APIs, and let me kind of do it here so it's just easier to do it in Visual Studio. So if we do like so, and let's just push it forward, and then we do offset, and then we move these things here, and again they go one by one because that's how we called them. Okay, so these are the offsets that we actually have to use inside of our assembly code. Now guys, this is probably, I kind of ran pretty quickly over it, so review my previous logic so I'm sure you'll get it, what I was, how I calculated these things. So just to make this video a little bit shorter, let me just go back and fill them in. So what I will do here, I will copy and paste them over here. Okay, so let's just go from dialog item, and it's very, very simple, guys. We just take this offset and just pipe it in, over here. Again, this is the offset from the beginning. And before we do that though, we have to do this little trick, because otherwise, yeah, it wouldn't work. So pretty much, let me just add this plus begin, which I didn't do in the beginning, because otherwise, yeah, it wouldn't work. It's just a simple refactoring. So definitely need it here, need it here, need it here and here. Now this one will treat differently. This one as well. Anything with RSP. Okay, command line also has RSP. Anything with RIP needs this. This is RIP, need to correct, because obviously there's a big difference between RSP and RIP. So over here I had a bug, it has to be RSP, and because of that let me check the rest of them. So RSP over here, which is correct. RIP here, RSP here, correct. RSP here, correct. IP, RIP, IP, and IP here. Okay, so now let me do get param. Okay, so got an offset here correctly. Let me do send message, and we use it in several locations. So replace this one, replace this one, and I think that's it. Okay, local free. Let me copy this thing. Now when you do copy and paste, obviously make sure that you hit Control-C and Control-V, and not just pasting the old value. Okay, get proc address and couple spaces. It's 4E8, 4E8. And then let's go back, and lastly we have get module handle. Let me see, 4DE, 4DE. Okay, so at this point, I think we have our APIs covered. And let's see what else we have left. So we have pretty much local variables like these. Okay, so this one is somewhat simple. Now, if you know how local variables work, they're basically some space that's reserved on the stack, and then you can probably tell by the presence of RSP in every single one of these. So what we need to do, we need to reserve space on the stack enough for these two local variables. Now, just as a small aside, guys, if you look at my original C++ code, as you can notice, there are quite a lot of local variables here, like this one, this one, this one, this one, right? And this kind of shows you how optimized code looks like. So from all of these local variables, it seems like the only ones that we have in the actual optimized code would be this one and this one, which is kind of pretty cool if you ask me. And this is also why I kind of let compiler compile my code for me, because as you can see, it's doing a fairly decent job. Obviously, if you have like 5 reverse engineers with a lot of skill working on it for a couple hours, they can probably come up with the more optimized version. But in this case, because this thing runs only once, we don't really care much about that to be, very optimized. Okay, well, that said, we need to see how much space we need for these values. Now, as you can see, an arg is a D word, so it basically needs 4 bytes. And also T button. Now, to be honest with you, I don't know how big this T button is. And the easiest way to find out is kind of like do this test, kind of like what I did before. If I do something like this, size of, well, you can do int, right, in case you don't know, plus size of T button. So in this will tell you what is the size of these two combined. So if I run and basically step over and check, the size is 24. So let me just put this real quick into my cheat sheet. So in other words, this is 4 bytes and this is 20 hex. And let's see, what else do we need? Oh, another thing that we need, guys, if you scroll all the way down, like over here, as you can see, we are getting an offset to one of the members inside of T button, and this is ID command. And if you don't want to calculate it manually, the easiest way to do it is if you copy it. Again, if we go back to my playground here, if we just do something like this, and C, I'm not sure if it's C or C++, has a really nice macro in Microsoft, which is called offset of. So first you specify the struct and then the actual member inside, and then if you run it and step over, this thing here gives you the offset, which is 4, and it's probably a second member. Yep, so it follows the bitmap, so that's why the offset is 4. So let's copy this and comment it out so that we don't deal with this later on. And let's just do here equals 4, right? So that's kind of like what we need. Okay, so this tells us that the size of the stack, the minimum size is a 24 hex. Now, to kind of like go along the x64 programming principles, I will round it up to a value that's divisible by 8, and this is technically the size of the stack that we need. So let's go back to our assembly code, and what we need to do is basically reserve this size of the stack before we start doing anything. And the way we do this, if you remember, the stack kind of grows down, so we have to do basically subtract the size from RSP. But before we do this, guys, there are two gotchas that we need to kind of like address here. One, if you go back to our original assembly code, let's see if I can find it. Yep, here it is. Over here, like original function, original window procedure, before it actually did all the restoration of these non-volatile registers here, as you can see, it put some result into RAX. And RAX, according to calling convention, is the return value from the function. Now this is important because the return value matters from the window procedure. And if you remember, we will be putting a jump over here instead of this instruction. So what we need in our code is preserve the value of RAX. And the way you can do this is by simply pushing RAX on the stack, like so. And then what you can do, basically reverse the sequence at the end before we actually do all this stuff. So we do add and we do pop. So again, we return RSP to what it used to be by basically adding what we subtracted from it, and then we pop RAX. So then when we do the final stuff that the original function was doing, we will return the RAX which the original function intended. So this is that. And one thing we have to be very careful over here is so-called stack alignment. Let me explain real quick what the stack alignment is. This basically says that when the function begins executing and goes through its prologue, its stack or RSP register has to be aligned on 16 bytes. And this is only for x86-64 Intel calling convention or ABI. And this is needed because many instructions inside that function may be expecting working with addresses which are 16-byte, that have 16-byte alignment. And if they don't have it, your process can crash. And the reason this is important is because over here we are kind of like creating a hole in the stack. So by adding this 28 hex numbers, bytes. And if we don't align our stack correctly, if we call some system function, like, I don't know, this one for instance, or this one, it may crash internally because the stack is not aligned. So in the way this works, now let's see if I can demonstrate for you, for instance, with the debugger. Like for instance, if okay, so send message here is enabled. So if I run my program and it broke here, if you look at RSP at the beginning, it is aligned on 8 bytes, but what happens afterwards, like let me just step a little bit forward. So when we pass through the prologue, like all this stuff here, and actually are inside the function, as you can see over here on the right where I'm pointing with the mouse, RSP is aligned on 16 bytes, which basically this last number is 0. That's what it means. It's aligned on 16 bytes. So over here, because of this push RDI and sub RSP 40, which is hex 40, this function or compiler in this case ensured that the RSP inside the function is aligned. So what we need to do inside of our function, inside of our shim, is ensure that at this point forward, the RSP is aligned on 16 bytes. This is very important, again, to prevent any future crashes. Now, let's see if this is the case. Now, we're obviously assuming, because, you know, the previous, let me show you, previous function was written by a compiler, that at this point when we made the jump, the RSP was aligned on 16 bytes. So when we get to this point here, right, at the beginning of our text to code section, we pretty much don't do anything except here we push RX, which subtracts 8, and then we do 28 hex, another subtraction. So 28 plus 8 will be 30. So in this case, we are at the correct alignment stage. If we were not, let's say if let's say we needed, like, for instance, 30 bytes, we would have to add a little bit of a hole to add a little bit more to ensure that we are 16 byte aligned. So make sure to do this make sure to do this alignment, because if you don't, it will be very difficult for you, especially in the beginning, to find out where your apps are crashing, your functions are crashing, and why, because they can crash totally, like, at some random spot inside one of the system APIs if you don't align the stack correctly. Okay, so let me remove this stuff. So let me make sure that I'm also adding 28 bytes at the end, and I am. Okay, well guys, I think at this point we're ready to actually put our arguments here. So it's very simple. So let's assume that RSP is and args is at offset 0. So we just don't add anything, right? And this TB button at offset 8. And over here, if you remember our cheat sheet, let's see, where is it? Somewhere at the very bottom. The offset of this ID command is 4. So we can technically do 8 plus 4, you know, kind of like to make it more readable. So this is the offset of TB button. And this plus 4 gives us the offset of ID command. Okay. Well, at this point, I think we kind of covered most of it. So at this point, we are ready to actually get machine code for our shell code. So what we do, we go from very beginning and go all the way till the end, including all the strings. Let's copy and plug it into our online disassembler. In this case, we have to assemble it. Most certainly it won't work from the first try. Okay, so it doesn't like the period. Let's see, where did we leave the period? It's probably somewhere in here. Okay, now first of all, I know that it doesn't like any comments, and that's probably where I put the period. So let me remove anything with the comment. Unfortunately, yeah, this online disassembler doesn't handle them well. So let me remove all of these things. And again, there's probably quite a few of them. Okay, let me try again. Okay, it didn't like H, and I believe, yeah, now unfortunately Visual Studio puts these H's, just try to search, instead of a hex numbers, like for instance over here, it's 0xf. Yeah, I just have to remove them and then copy and paste it into Notepad, like also over here, in case I have to modify something again. And this guy also needs to be replaced with this. Yeah, it's like a real quirk, like a weird quirk of this assembler, and let's do it. Okay, here you go, it worked. So let me copy this and I put it here. So we have it for future reference. And what is important for us is that we got this bunch of machine code that literally basically does all of our, basically is a translated assembly code. So, well, what we need to do is actually put it into our text2 section. You'll like find it here. I don't know exactly how you can do it in x64dbg. The way I usually do it is by using the xd hex editor. So the first thing we need to do is actually locate our section. If you remember, we added this magic sequence there. And let's make sure that it's not found anywhere else. Okay, so this is where our section begins, and this is where we need to add our machine code instructions. As you can see, there are quite a lot of them, and because of the quirk of the hexd and the way it accepts input, I have to modify it really quick, remove all of these things, basically commas and 0x in the beginning. Luckily, it's really easy to do with replace options. So we're replacing this with the space and replace all, and then replace the first one. And this gives us the full machine code. So make sure that you put your cursor in the beginning of the section, go to edit, and paste right. Make sure it's not insert, but paste right. And we got our machine code. Let's make sure we have 31FF 4889. Okay, and at the end we have 655700. So at this point we can save it, but we're not done yet, because what we need to do, if you remember in the very beginning, we have this the ending. So what we need to do, we need to put a jump over here so that it can actually jump into our text section. Now to do it really in an easy way, let me see, did I save? And I did not save the offsets, so my bad. So basically we need to know the offset of this line, but it's not a problem really. So let's open it. Let's see, let's open it in IDA, I guess. And so again, have to do this thing real quick, load symbols. Now this part is really simple. While it's loading, let me show you what we need to do. We basically need to put a jump instruction with a really large offset. And let's see, what am I doing wrong here? Oh, always put it in the wrong place. So if we do jump instruction, this is literally the code or the machine code for it. So over here, we need to place jump, and this is the offset that we need to calculate from the following byte. And this is what I will try to do right now using debugger. So let's put a breakpoint over here. We've done it many times. So let's run it. And you know what, guys? Hold on. IDA is not very good at this kind of stuff. My bad. So let me use xdbg, because we need to see all the sections. So if we go here, run it. So we need to put a breakpoint on Snipping Tool. Let's see. There should be a way to load symbols. Download symbols. And what we're looking for is this symbol. If you remember, that's how we that's the name of the window procedure that we're putting a shim on. Oops, now what did I do? Hang on, not so fast. So toolbar dispatch, yeah, I think that's the correct symbol. Okay, so let's make sure that this is where we are putting our breakpoint. Yep. So this is the address. Let me kind of copy. Okay, like first of all, let's see the size of the instruction, and this is 1, 2, 3, 4, 5, and it will be placed on this line. So this is 1C9A is the address. Let me just put it down here so we don't confuse it. And then we have this instruction, so it will be A, B, C, D, E, F. So let's say whatever the next byte will be F. So like so. Okay, and then we need to get the offset of our text section right in our module. So let's copy address 45 and 4 zeros. Okay, so and then all we need to do, we need to take this, and I'm sure we can do it in a calculator. We can do this and subtract this. And this will give us the offset. Okay, let's see, can I just do that? Oops, nope, I can't do Control-C. That's a stupid calculator. I just have to highlight it and do this. Okay, so this is the actual offset to our module, and what we can do is just try to convert it into machine code instructions. Oh, doesn't want to do it, but okay, we can do it manually, really. So it will be E9, right? So we're just doing it in reverse order. So E9 is the instruction itself for jump. Then we do 6-1. Then we do E3. And 32 and 00. So it's kind of like basically the lowest byte goes first. So 61, E3, 32, 00. And this is technically our patch. So let me remove all the stuff. And yeah, so we just need to put a jump over here. To locate that instruction, we need to copy, let's say patch from, and then we do patch to. Now to locate, now guys, when you start searching by this stuff only, because this is the epilogue of a function, it will be found in many locations, so you need to include a little bit before it, and that's why I'm adding a few bytes from here to add a little bit of entropy. So if I do this, and let's say one of these, so let's make sure that we can actually do it, and what I need to place it at is right here, right, instead of this instruction, and this has to remain. Okay, that's why I aligned it like this. Okay, so well, we've done it many times. Let's locate this sequence and just clean it up so we don't need debugger anymore. Okay, so we open our snipping tool in hex editor, and we try to locate this specific sequence, and we need to make sure it happens only once, and this is correct. And so let me kind of bring it down here so we can actually see what we're doing. Okay, so instead of 48, 8B, 5C. Okay, so we need to patch it with E9, 61, E3, 32, 0, 0. Now make sure that the sequence is correct, because if not, the app will most certainly crash. So E9, 61, E3, 32, 0, 0. I literally took it from here. Okay, let's save it. And at this point, well, I guess if you're really brave, you can run it. I probably would step through it with the debugger, and because at first you will probably create a lot of errors there. So let me load it in item and actually step through it to kind of see if we made any mistakes so that we can actually correct them instead of dealing with the crash dump. Okay guys, you've seen this process probably many times. Okay, so I'll let IDA finish its thing. I'm going to put a breakpoint in the beginning in Win main, run it. So the next thing is to load symbols for the snipping tool, because we'll definitely need them. And if you remember, this is a function, so we need to get to it. Make sure to put a breakpoint before you actually let it run. And let's see, add breakpoint and run the app. And let's see if it has a patch here. And it does. You see like this jump here at an even address. So I'm going to put a breakpoint here, because in the beginning I'm not confident if it will get to it right away, so I don't want to step through it. Let me remove the old breakpoint and wait until my new one hit. Okay, so we're at the jump, so let me remove it. Actually, you know what, let me just step into it and see what happens. Okay, so we are in our text 2, as you can see here on the left. And let's see, so RAX is 0, let's push it, and then we create a little bit of a hole in the stack to work for us. So RSP, as you can see over here on the right, is aligned on 16 bytes, which is correct. And we have RAX as our global variable. Let's make sure that it's actually readable and writable. So I hit G and RAX here, and sure enough, it seems to be we're at the end of the section here. So let's see, our EDI is 0. So at this point, it steps in because it's 0. Okay, now R14 is the message, and it is 0 at this point. So, okay, so we step over, restore RSP, restore RAX. We restore the rest of the registers. And, well, we go on our merry way inside user 32. It seems like we haven't crashed yet, which is nice. Let's run it again. And let's, at this point, let's remove this breakpoint, because we'll set another one. Step in. You can do the same thing. As you see, our RAX value here at the bottom, which is this thing that I highlighted, is still 0. And the message, R14 in this case, is still 0. So to avoid stepping through, like many iterations, let's put a breakpoint here when the message is actually our window message paint. Let's run. And we did not hit our breakpoint. So that tells me that we messed something up. Let's see what is wrong here. Okay guys, this is very stupid. You see, like R14, where a message is supposed to be, it comes from here. We take it from ESI, but ESI, right before it, is taken from RDI, and RDI is zeroed out. So this is put in complete wrong order, and that is why it doesn't work. We basically just set all these registers to 0, which is really stupid. So all we need to do is like put them in correct order to make this thing work. So sorry for this. So let me correct it real quick. So I don't want to change anything because we'll have to patch our binary thing again. So let's go back to our code here. Actually not here, but where we saved it here, already edited. Okay, so over here, well, let's just look at the comments that we made. So R14 is the message. And we set it first, right? Then, if you see over here, RSI is the window. This part is really interesting. Actually, we have to do it like so. Yeah, hold on. Why am I doing this? This makes no sense. So EDI has to be 0, and our window. Yeah, hold on. I removed all the comments, so let me kind of go back here. So RSI. Let me make sure one more time. Yes, so RSI is our window, right? So we need to get RSI from RDI here before we reset EDI to 0, right? So RSI is the window, and R14 is what we get from ESI, and then we reset EDI to 0. So I think this is how it's supposed to be. Yeah, guys, this is the sequence. As you can see, I kind of didn't think about it. I just quickly pasted it in here. And this really makes a big difference because RDI on the input is the window handle. So we need to put it into RSI like we expect further down. ESI is the message that we receive here, but we need it in R14D or lower register. And then we have to reset RDI to 0 as we expected here. So this is the correct sequence. So let me take it and put it over here. So now we basically need to compile this thing again. Make sure I save it. So we go back into our online disassembler. Now I can most certainly guarantee that you will make a lot of mistakes, especially if you do it for the first time. So don't just run your binary, because most certainly it will not work. But this way, when you do it with the disassembler and compiler, you can actually quite easily see the problem. So I copied it here. Let me open it in Notepad and remove this stuff here. So let's see, replace this with the space, replace all. Okay, so I think we have 48 in the beginning. I'm going to double check. Yep. Okay, well at this point we need to locate our section. It doesn't have a magic stuff there, so we can just take anything on the middle here. Open it in hex editor. Do find. Okay. We can kind of tell that this is a section. We don't need to change anything. We just need to put the cursor at the beginning where it says 00. Then We need to get to our notepad with the machine code. Take all of it and paste right. Save it. Okay, and let's try it again. So again, the same process applies. We open an item. Let me just do it real quick. Load symbols. And before it's looking for it, let me get the name of the function. The reason I'm not saving it in IDA is because of some weird bug in it. If I change the binary code, it will not show correct disassembly, so that's why I have to start over after a patch. Okay, so let's load symbols for this guy. Oh shit, what did I do? Let's see. Control F. Put breakpoint and let it run. Okay, remove the breakpoint from here. At this point, we can just jump to this one. And just for the heck of it, let's put a breakpoint here and see if it works. Okay, so you just look up my RAX, because RAX is the global variable here that keeps the location of our variable, whether the app, where the chunk ran or not ran. And let's see, R14 in this case is not 0, so it actually has some value. And let me put a breakpoint here and remove it from here. And I'm messing it up again. Now what am I doing wrong here? I mean, let me check, guys. So I put a breakpoint. It should technically hit right away. Okay, so ESI R14 is the message, right? And R14 comes from ESI, which is RSI. So RSI looks like, let's see. Okay, R14. Now, why is it? Oh, seriously? Okay, guys, I need to take a break. Do you see, like, over here? You see that this ESI in this ESI, so in other words, this has to be in here. I don't know how many times I need to do this. Let me check this. Hang on. Yeah, this is the correct sequence. In other words, I put this on the first spot, and it shouldn't be. So, well, take 3. Again, as you can see, I'm recording this live, so I'm kind of showing you the process. So, yeah, it's not really glamorous. It takes a lot of time, and you make these like really stupid mistakes. Because again, you see ESI, but I kind of override it here. So I have to reverse these two. And pretty much repeat it again. Luckily the process is somewhat straightforward, so again, if you want to like skip about 10 minutes forward, I'll finish this mundane task. And I can only hope that I can not make the same mistake again. And let's see, notepad, copy, I think it remembers what we were replacing. Yep, replace all. I have to use something like this to actually locate it in the binary file. Okay, so here's our stuff here, and I need to place all the stuff in there. Okay, save. Okay, well, take 3. Let's see if I fixed it this time. Yeah, it's like really silly error, and that usually happens when you kind of like, you know, rush things, and yeah, so 3 times is a charm probably. So let me get function name. Okay, yeah, it takes longer and longer. I'm not sure why it's so slow. Okay, so get here, load symbols. You've probably seen it so many times, but again shows you the process of reverse engineering. Okay, put a breakpoint, run, and let me remove it from here. Go to my thing, my patch here, put a breakpoint, get to it. Okay, so ESI is 24, which looks like a window message. RDI is what looks like a window handle. So R14 is our message, and RSI becomes our window handle, and EDI is zeroed out. Okay, fingers crossed. So let me, well, first of all, let me get to RAX here so that we see the memory. Again, it's this location. And at this point, well, let me put a breakpoint here, and fingers crossed. Okay, and we hit it. So right now we are inside, and we're ready to do our button simulation. So let's see. First of all, RAX is set to 1. Okay, perfect. Now RCX should be the name of the module. It starts from here. Again, some kind of bug in IDA. This is S, so shell 32 DLL and nulls at the end. Okay, I'm not sure why it's showing like so, but let's see. Ooh, and we crashed. This is not good. It means that my input address table is set up incorrectly. Okay, well, let's see, what is the issue? So in this case, I probably set the offsets incorrectly. So let me look at the assembly code. And it seems like that this is all of them. If you look at like this one, this one, this one, if it was the actual API, it will be written in blue, I think. So yeah, definitely there's a problem with the offset. And let me see what is the issue here. Oh, well guys, yeah, do you see right here? So basically, if you remember, if you look at our sections, the one that our code resides is in here, right? And our, I think the import address table either here or here in one of these sections. So in other words, we have to subtract the offset and not add it. You see, like over here, I did actually the right thing, but over here, I did not. So pretty much anywhere where we have this begin, I have to subtract my offset and not add it. And this is another example how you can really screw yourself over if you don't pay attention to what you're doing. And it's especially true if you're trying to record it. I'm not trying to justify myself, but it's, yeah, like these kind of dumb mistakes that you make that really kind of show. Okay, well, let's double check again. So this one is minus, minus, This one is minus. Pretty much any call that you see. I'm sure you're probably yelling at me if I missed it somewhere. Okay, this and this. This and this. And okay, well, take 4, right? Now let's see how many times it would take me to actually make it work. So, copy. Okay, we need to stop item. And close it, don't save. Okay, so let's go here. Paste it, assemble. Let's make sure that we get all of it. And we need notepad. The good thing is that remembers the previous selection, so I can do that. And as you can see, this patch is fairly large. So let's use some sequence inside to actually locate our code segment there. Okay, so let me put the cursor in the beginning. Take all of it. And then we go edit, paste right, save, and rinse and repeat. Okay, so let me get to the point when it's loading. And yeah, you've seen it like 5 times already, so let me get the name of the function. At least I'm getting somewhere, you know. It would be bad if things were just like totally off, and at least some of those offsets are correct. In this case, because of some stupid like typos, I can't call it any other way. Just using, you know, plus instead of minus. You guys have to sit through all of this. Okay, so let me locate the function, add breakpoint, run. Move breakpoint. At this point, we know that it kind of works, so we won't be checking any of this thing. Why is it get process heap? Yeah, there's still some kind of issue here. This is not a get process heap, so I need to check my my offsets again. Yeah, these offsets are most annoying, and if you get something wrong, it seems like by just a few bytes here, you can actually get all kinds of issues. But well, let me try to run it. Sure, this thing will crash. Yeah. Okay, as you can see, the getProc address is correct, but this first API is not. I'm off by a little bit. So let me check down here. So get dog item, send message is correct, local free is correct, but I somehow messed up this first API. In the first API, if you look in my thing here, is get module handle. Interesting. Let me see, what did I screw up this time? Let me get to it, and yeah, it's right here. Okay guys, I did this behind the scenes to kind of quickly review this, and this offset is wrong. So my mistake, if you remember when I was getting offsets from, not offset, but the address of the call instruction for, in this case, for get module handle, what I did, I got the address of this instruction instead of the following instruction. That is why I was literally off by the size of the call. So I kind of like looked over my notes, and basically this offset is a little bit off. So this has to be D8 and D8. Because of that, well, just me rushing basically, I was off by a few bytes, and that is why this offset did not work. So I already lost count how many times I tried to recompile it, so let's try hopefully one more time. But again, that is the reason why the offset was wrong in the import address table. So unfortunately have to start over. And again, you've seen it many times, but it kind of shows you the process, so that's why I'll probably not edit it out. So, okay, we've seen this before. So we take this machine code sequence and just basically format it. Jesus Christ, seriously. What is it doing? Am I like... Wow. Okay. Even Windows is acting up. Let's say replace all. And get some random sequence here. Okay. This is where we need to place all this stuff. Paste right. Yeah, it's just literally two small offsets, so let's see if it works better now. Okay, back for the function name. Let's see, where's that sucker? Here we go. Okay. I'm not sure if either me getting faster or either getting slower, so it's one or the other. So get here. Come on, load symbols. Double click, Control F, locate a function, add breakpoint, run. Remove it from here. And at this point, yeah, you can see right away that I got the name correctly. So, well, let's just step through it. Let's put a breakpoint over here, run, and we hit right when the first window message was processed. So you can see this value at RAX, our global variable, is set, or will be set to 1 over here. So let's see if we can get our module handle, and great, we got the module handle. So then, as you can see, IDA helps us get command line to argv, if we can get proc address from it, and great, we got it in RAX. Let's keep going, and again, as you can see, when everything is right, IDA actually shows you. So we have kernel 32, and yep, we got its handle in RAX, and then we try to resolve get command line, and let's see, yep, we got it as well at RAX. So it calls, let's see, yep, it calls command line. Now unfortunately, guys, over here we don't have a command line, so if I do gRAX, our command line is just the executable itself, like over here. So if I scroll down, you see there is nothing following it, so our patch is not going to work in this case, but let's still see what happens. So then we actually, in RDX over here, we store the number of parameters in command line. So let's see if that would work. Yep, and we have only one, which is correct. So then we need to go through them, and in this case we are checking, let's see if we go RCX, we're checking what do we have on the input. No, I'm sorry, so that's the first, it's a pointer to the first parameter, so RDX, to the first command line, our dx contains it. So in this case, it's just the path to the executable. So in this case, it would not work. And we step out from our if statement and from the loop. We call local free, which is success because it returns H result. And so we continue running, step out, and if I let it run, obviously nothing happened because we didn't have a command line. But as you see over here, the snipping tool works and is still alive, which is a good sign. Okay, so what we need to do, we need to give it a command line. Let me see, process options, and parameters is 1, if you remember our command line. In this case, let's start it again. Our breakpoints should be intact, so let me double check. And sure enough, so we hit the breakpoint. Okay, we know that all this stuff works, so let's just kind of step through it quickly. Okay, so what is interesting is over here, when we get, let's see, memory at rdx, like, you know, this parameter that we're passing into the function. And again, we look here, and let's see how many command line parameters it would give us. And we have 2. Okay, awesome. So far, so good. So let's see the first one. Let's do grdx. And again, this is just the path to the process itself, so that wouldn't work. And we should stay in the loop, and we get the second parameter. Let me see, g at rdx. The second parameter is 1, so technically our if statement over here should work, and we should jump. Okay, and we did. So next is, okay, our RSI is the window handle. Looks like it's valid, and we get control with ID 1. Let's see if it will return us. Yep, it gives us a window handle for the toolbar. Then, if you remember, next call, we scroll up. Let's see, where is our patch? Next call, we need to fill in the TB, you know, button with this send message. So let's see what would happen. But before we do this, in R9 is the address on the stack. So let me just kind of like point it up here. So it should be probably like all of this stuff. So when I go through send message, it should fill out all that information for us. Let's see if it happens. Oops, sure enough. I mean, oops, like sure enough, it did. And then we are getting ID of the control in R8. And it's of that button, it's DB, whatever that is. You can actually check. Probably gave it some kind of round number. DB 219. Okay, maybe not. But anyway, so we got the ID of the button. And the next thing, it should actually send the message to begin the snip. So in this case, it might hang up the debugger, but let me check. Okay, so we sent the message, and then we do local free to release the memory in RCX, and we should return 0, and we did. And at this point, we restore everything and return. Okay, so if we continue, yeah, we got a snip. Okay, guys, it seems like it is working. Now the final test. So let me close this thing. In this case, let me save IDA. And again, I'm keeping the crash dump folder open in case this thing crashes. So hypothetically, when I run it, nothing will happen, right? Because we don't have a command line. But if we create a shortcut and call it, let's just call it auto snip, and then go into its property, and over here at the end, after a space, we specify a command line parameter. So technically, if we run this thing, the snip should start automatically. Okay, and it is working. So just to kind of like make sure it doesn't crash many times, let me just do this, keep it open, do another one, and do another one. Yeah, so it seems like it is working, and it seems like this is the end of my three-part fumbling, I guess, over reverse engineering and patching of the Microsoft Snipping Tool. Now, I know, guys, this turned out really, really long, so we'll see if YouTube will allow me to upload it, but this is basically the process. I literally showed you, kind of like without any cuts or without any, editing, how the process works, and if you watched it up to the end, you kind of know the gist. Please understand that this is kind of like an art form. There is a lot that goes into it. There's a lot of mistakes that you can make. And at the end, you get a final product. So again, thank you for watching. Thank you for sitting through these long and tedious three parts of reverse engineering and doing binary patches. And in the next time, we will do something else. So see you then.